in our mini course series. This is a Q&A for Patreon members and for the live public. I'm hoping that it says it's starting live preview right now, so I'm hoping that we are live. If not, this is just on the replay, then hello replay viewers. I hope you're enjoying this thus far. Oh, I can hear it on my other computer. Good. Let me try to turn this off. Okay, wonderful. So I think we are live, and I'm very excited to be able to show you kind of my new digs here. I have a television that I usually use that's actually over there that is on the fritz. It's beginning to die. So I decided to try something different. As you can see, I'm actually kind of live on a green screen. And this is new. We'll see what you guys think of it. It's the first time I've done a live green screen. You can tell it's not quite as well etched out as my higher productions during the, when I put my forecasts out. But hopefully this will be good and it'll work for you. And I probably should see if I can check. If I flip to the back with my computer, I'm afraid it's going to show that that you're going to see my video behind me, which might be very odd, and I might have to do that because I can't get it on my phone. So hold on a second. I want to make sure everybody is hearing me and seeing me okay. So let me do this. Are you guys seeing me? Let's see. Cheers. Hopefully this doesn't look too weird. Cheers. Let's see. Wichita, Kansas. Yes, all working. You are live. Wonderful. Woohoo, live. Okay. Oh, wow. Looks nice. Your backgrounds look nice and bright colors. Good. Everybody likes it. Excellent. So if you can handle the green haze and sometimes seeing your own chat up here on the screen, I can be able to talk to you guys live. You see a double picture of me behind myself. If you can handle that, then we'll do that from time to time, and I'll see if I can scroll through some of the chat and answer your questions. So hello. We get this beautiful mirroring effect. I'll try to stand in front of it so that it doesn't, see, is this way or this way? I can't tell because I'm mirrored right now. But we will have some fun with this today. Before I jump into it, let me, for those of you who do not know who I am, my name is Dr. Tamitha Scove. I am a PhD space plasma physicist, scientific researcher who has spent, oh my gosh, the last 15 years working essentially in industry, doing things like keeping space assets safe for agencies like NASA and NOAA and other agencies as well. So I know a lot about space weather. Oh my gosh, I'm going to get this off this now. I'm going to go to the sun really fast. And what I did a long time ago is I decided to reach out to just the average person, just the normal people out on social media, and to see how space weather affected them. And the amount of support I've gotten has been overwhelming. So many people use space weather every day. So many people are making it part of their lives every day. And so it's just becoming so much more critical to really essentially understanding what weather is all about. It really is the weather of the 21st century. And today's class is going to be the continuation of a two-part lecture on coronal mass ejections, which are basically solar storms. And I guess our sun is really cooperating because we've had this one region. If I can figure out where to point, this one region right here, 2734. That region is what we call a rogue sunspot. And it's the reason why we call it rogue is because it doesn't really belong to solar cycle 24 or to 25. It's kind of in between. It emerged at too low a latitude for us to really officially call it a cycle 25 sunspot, but its polarity is kind of bent. It's not emerging with the polarity we would expect, but it's also not emerging with the polarity that is assigned at cycle 25 either. It's literally halfway between them. So instead of either having a leading and trailing field pointing east-west or the other way around, your cycle 24 and cycle 25, it's actually got a polarity that points kind of north-south. And so you can tell it's very confused. It doesn't really know what to do. So we call these sunspots rogue sunspots. And the very interesting thing is that it is unstable. It's acting kind of like a cycle 25 sunspot because it is firing off solar flares and coronal mass ejections. So it's very apropos to this talk. And I will give you just a really brief weather forecast so that you can see, because we have, it looks like two Earth-directed solar storms coming our way. So when the movie resets, there you go, that was the moon that passed by. You can see region 2734. I'll try to get back to, I got to learn how to use this. There we go, boom, do you see that? That was a solar flare from that region, and it also launched a solar storm, or what we call a coronal mass ejection, our way. And then boom, right there again. Did you see that? It also launched another one. So we have got potentially two solar storms that are Earthward directed. If I switch, let me stop this movie here. If I switch to I'll switch to Enlil. This is NASA's version of the model. You can actually see the solar storm. Oh wait, they already changed it. Oh, you guys, you changed it already. Are you kidding me? All right, I'm not going to do that. These guys have to catch back up. They had a solar storm that was launched that that looks like, and I do have a copy of it, I just don't have it up, that looks like the eruption, the ICME is going to, the coronal mass ejection is going to reach us, like they say late on the 11th. Now, NOAA has done their version of Enlil. Enlil is the solar wind prediction model, the solar storm prediction model, and you can see as it launches out like that, you can actually see what looks like two different eruptions. Oh, I'm standing in the way. Hold on, let me stand this way. I got to get used to this. Hold on, let's see if it starts over. Yes, okay. So hopefully you'll see in just a moment, you'll see two solar storms coming out in this direction over here. There you go, 1, 2. Looks like NOAA has caught two different eruptions because it was kind of a two-parter. Not exactly sure how well they were able to resolve the two parts of it, but it looks like they're definitely trying to. NASA's prediction model, for those who have seen it, looks like they've caught the second half of that eruption as opposed to the first half. So NOAA actually has something arriving right before the 11th. So we have, unfortunately, between the two models, we have kind of a day in between. It's you know, a window of about a day between late on the 10th into the 11th and maybe late on the 11th into the 12th is when we were seeing maybe intensifications. That's going to be due to these solar storms that will be hitting Earth. And it does look like they're going to be weak storms, so I'm not expecting a whole lot, but hey, considering it's solar minimum, this is wonderful to see. So I will be putting out some official forecasts shortly and some forecast graphics on Twitter that will show these models and maybe show the difference between them so you guys get a better appreciation. But this is a perfect subject as we launch into this second part of our coronal mass ejection mini course series. We are now going to be moving away, just as the model shows here, we're going to be moving away from the sun and into the solar wind with these structures. So you will get a chance to see how do we detect them in and around Earth. Why do we find it so challenging to be able to get their magnetic field orientations correct? And you know what, I can even pass on some information to you on how to actually use the magic of prediction on your own for certain structures that are predictable, because not all of them are. So let me go ahead and stop this, and I'm going to kill this stuff so that we don't have too much going on here. And let's see. And let me just check again to see, okay. Oh, Jerry, hi Jerry, you're here, and Notani is here too. So I've got a couple VIP members. I'll flip to them and say thank you. You guys are definitely helping sponsor all of these. And let's see, March 12th to reach Earth. Your prediction? Yeah, you know, we may have that. It may take till the 12th, because they had said in the NASA model, the solar storm had said that it would be hitting us right around you know, the end of the 11th. So we'll see. But remember, NOAA has a prediction that's actually showing kind of a two-part structure, and the early part of it is going to be reaching us by the 11th. So just be aware, it could arrive early for those of you who are thinking it's going to arrive much later. Now, to get out of this here, I'm going to stop this, and I'm going to go, hopefully, to this presentation. Okay, let's go back to this. So officially to start now, I'm going to take a quick sip of water. This is the live Q&A mini course called Interplanetary Coronal Mass Ejections and the Truth About Carrington Events. And it is sponsored by members of my Patreon community. I absolutely adore you all so much. Your conversations on Patreon have really helped just expand my world. They're the whole reason why the little forecast shorties that we used to do have now become space weather news. And we are extending into the realm of orbits. We might be extending into the realm of Mars, especially as activity picks up. And poor InSight lander is having so many troubles right now. I feel badly if a windstorm knocks it over. But these types of things are becoming a bigger issue. So the space weather news section is expanding to be broader than just a solar storm forecast. And I have you Patreon members to thank for it. Special big thanks to the VIP committee. If you guys can see, I'll back up a little bit so you can see yourselves here. Thank you so much. And then all of my mini course patrons, you guys are the bread and butter of these courses. And as you can see, I am now using a green screen. So make sure you let me know if this green screen works, if it's not too tacky, not too 1970s, you know, psychedelic man kind of thing. And I will continue to use this. It could be very, very helpful for continued discussions. Okay. So hopefully some of you caught the previous part of this course. This was the one that had to do with coronal mass ejections, the history of them, how we first observed them on the sun, how our understanding of them grew based on our observations. But because the course, even as it was, the course took 3 hours for me to finish, which was awful. I'm so sorry. But I had to stop because I couldn't get out to the solar wind. It just was too much information. So we split the course in two, and now I'm moving out into the solar wind. Hopefully this one isn't going to be nearly as long. I do have a lot of charts though, so we will see. But I'll try to be a little bit more on target. So to kind of remind you and get you oriented, we've got 4 basic phenomena that affect Earth. We've got and they all are very, very different. We've got solar flares, which you can see one right there up in the left. And then we've got the coronal mass ejections, which you see off onto the right top. Is that going to be the right top? No, it's going to be the left top, my fault. Left top over here. Then we have coronal holes, which drive fast solar wind. And then we have radiation storms, which I'm standing in front of right now. And today we are going to be talking about coronal mass ejections, but we are going to be talking about them as they drive away from the sun. So they get out of both the disk view, that's what we call this, the far left view with the sun right there, and then even beyond the coronagraph view, which is as they leave the solar atmosphere. So we can no longer see them in white light. They become so tenuous that it takes special instruments to even get a whiff of them in white light. And I'll show them in just a second. But they're really hard. It's really hard to do real-time monitoring with that. So we actually have to go to completely different instrumentation called in situ instrumentation in order to even know they're coming at us. And that gets really tricky, and you'll see why very soon. The other thing is that these coronal mass ejections, they do drive radiation storms. Both solar flares do and coronal mass ejections. They drive radiation storms, so I will be touching on radiation storms a little bit, especially when we talk about the Carrington event, because there are some implications of the radiation storm driven by that coronal mass ejection that's impactful, that matters. And we've seen it in the past, and we will definitely see it again. So let me move on to the next slide here. And again, this is just to kind of get you oriented. I'll stand on this side. We have a quiet sun, right, where basically we just have solar wind with some high-speed streams, fast and slow wind, pretty much what we have right now, except when we get a rogue 25, or maybe new cycle sunspot trying to get its way in there and cause some ruckus. But usually during solar minimum, we have a quiet sun with high-speed streams and sometimes some interplanetary shock waves, because when those fast wind streams hit the slow wind in front of it, it can drive a shock. But with the active sun, we get solar flares, and I'll play, hopefully this will play for you. You'll get a solar flare, which I will talk about in a separate course. That'll probably be the next course that we do. And then those release X-rays, and they have a lot of electromagnetic light that travels. Are you coming or what? I'm not sure it's playing. No? Let's go back. Hello? Why did you not play? That's interesting. Hopefully it's going to play. There you go. There's a flare, okay? And then, but those don't drive the coronal mass ejections necessarily. Coronal mass ejections, which are these big solar storms, they can be launched with flares, but it doesn't have to be, right? So a coronal mass ejection, oh, as I'm standing in front of it, let me show you. Coronal mass ejection, over here, you see it coming out, and you'll see it blow out into the solar wind from the sun. This is what I'm going to be focusing on today, this stuff here, okay? You can see that coronal mass ejection blowing out into space, and I will go ahead and stop this right about there. And the reason I'm stopping it there is that you can actually see the loop. Do you see that loop? That loop is really the reason why us scientists have any chance of predicting anything at all. Everything on the sun is magnetized, and that means that there are magnetic fields, there are electric fields, all the particles are charged. It's a plasma, which means basically it's a gas that's charged up. And the cool thing about that is that it means that all of the particles that are there, all the material, all of it sees magnetic and electric fields, and it has to obey them. So they become like a jail bar, right? Like if you have a coiled magnetic field, and hopefully you can see that good, you can. The coiled magnetic field, just like what you have in your slinky. Particles will have to chase down that coiled magnetic field. They'll have to actually use it as like a track. Imagine like Hot Wheels cars, and that's the track. And the particles actually have to follow that. So they are jailed inside and along these field lines. These are magnetic field lines that are twisted and turning all the time. And that really is why we have a loop at all. So when you see that plasma coming out in that coronal mass ejection, and I have no idea if I can do this, if I can move it over here. Ha-ha! Look at that. Green screens are fabulous, aren't they? Woo! You're looking at a slinky, kind of like this. Let me take that down, you can see. See it? Actually, it may be up a little. Maybe pointing up. Move it back over here. Maybe more like that. Set it down, yeah. There we go. So if I take that slinky right out of there, that's what you're looking at, believe it or not. You're looking right down the pipe of that coronal mass ejection. And yes, they look like slinkies. We call them solar slinkies. I can thank Spiro Antikos for that. So this is what we're going to be talking about today. They are massive amounts of solar plasma and enhanced magnetic fields. They drive strong shock waves in space, and they take about 2 to 5 days on average to cause storms at Earth. Now the fastest ones can actually take, I think the fastest one only took 14 hours to reach Earth. That's like half a day. So we do get really, really, really big ones, but they're reasonably rare. But we have had them in the space age, and I'll talk about them. As we move further out, you see in the coronagraphs, these are white light coronagraphs, and you can see them. I talked about them last time. Those are coronal mass ejections being blown out into the solar wind, and we can still see them very easily in white light because they're still very close to the sun, and they're not expanding. Okay, it's a lot harder once you see them getting expanded. Now, one thing I'll wait for is the blizzard. There you go. See that blizzard? Those are radiation storms. And those are being driven not only by the flare and the actual events on the sun, but they're also being driven in space by the coronal mass ejection itself and the shock wave that's in front of it. And we will talk about that. Now, if I go down here, this is the HI instrument that I never talked about before. As you can, I don't think I did anyway. You can actually see that you can look at coronal. There's a big coronal mass ejection that just went south. You can actually see those eruptions, and we can actually follow them all the way out to Earth, because at one end of one end of this is the sun, and the other end of this goes all the way out to Earth. So we can follow these structures all the way out to Earth. It's just very difficult to do it in real time, and the reason for that is because this data is it's massive. You can't really telemeter this from behind the sun or as far away as stereo is and get it all back to Earth in time to be able to make predictions. It takes days and days and days for this data to come back. So it becomes very, very difficult for us to be able to do these types of predictions in real time. Yet, right? We'll get there. So I've kind of gone over what coronagraphs are and how we got 3-part structures. You can see down in here is a beautiful 3-part structure, and the reason why I'm reminding you of this is that this gave us early hints as to what the actual structure might look like when it reaches Earth. Let's see if I can put the thing back up here. Come on, up, 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 over. There we go. It's a lot bigger, so I have to pull this out this way. But this thing, oh geez, I can't do it. But this thing is, again, a structure that's coming out like this. And we started getting models of it, right? So you can see some modeling if I move over here. And we started kind of looking at how these structures blew out in the solar wind. Again, all of this is in the prior class. And then we got even better at our observations and started being able to see not just surface features like filaments, but then we got EUV imagery and we got X-ray imagery, and we really started being able to create these models of these structures. Let me stand on this side. So again, this kind of looks, if I'm looking at this right, yeah, this image looks a lot like the image that you saw on that coronagraph, right, with that three-part structure. And if I take that image and I flip it upside down, now you're kind of seeing that loop. And there's a reason why I flipped it upside down. Don't worry about reading the words, because their words are upside down, I believe. Yes, they are. But I flipped it upside down on purpose because I want to orient your mind. Because as this structure continues to evolve and pull away from the sun, the feet may still be anchored to the sun, but the bulk of this structure continues to move out and expand and get bigger and bigger and bigger as the solar wind kind of takes it off and blows it off along with the solar atmosphere. That's all the solar wind is, by the way. It's just simply the part of the solar atmosphere that manages to escape the sun's gravity and participate in solar wind expansion. So what we're getting hit with when we're getting hit by a solar wind, we're getting hit by a part of the sun's atmosphere that left. Pretty cool, huh? Okay, so keep looking at this way and just imagine in your mind as it begins to expand out. What might it look like? Well, maybe something like this. Does that look familiar? So basically you're just looking at that same loop, and I can't tell where I'm pointing because my key is behind me, but you're just looking at that same loop, but now it's moving further and further and further out. But here's the cool thing. Do you notice how there seems to be like some wiggly lines kind of threading it? What do you think those wiggly lines are? Look familiar? Do they look a little bit like this? Wiggly lines? Yeah. I can tell the slinky isn't doing quite so well. But this is the same kind of idea. You have got essentially a tube, what we call a flux rope, in the core. Whoops. I wonder why it did that. In the core of this. Hopefully that went back to the right place. Yes, good. Notifications for some reason turn off the PowerPoint. So that's really what we're dealing with, is a flux rope structure, is a rope-like structure. And I'll talk about this structure a little bit more, but just keep that solar slinky in your mind. Now I'll see if I can stand, I don't know where I can stand, maybe back here, so that I'm clear of this, because I need to talk about this diagram a little bit for you. And yes, I'm trying to take sips of water to save my voice. So what you're looking at, you know, when you look at something like this, the problem is with this structure is that it's far too tenuous for us to see with our eyes anymore with cameras, unless you have that HI instrument that I showed you before. But even then, you're not really looking at the magnetic field of the structure. Magnetic field is completely invisible to the eye. So how do we get an idea of what this looks like? Well, we basically have to fly through it. And when we fly through it, well, why not fly through it with instruments that can measure the magnetic field directly? And so that's part of what the instrument suite, the suites do in these in situ payloads on these spacecraft, is that we actually we don't just take cameras up there that can look at things from a distance, what we call remote sensing. We have instruments that can measure magnetic field, measure plasma, the actual density of the plasma. Even in a vacuum, it's not quite a vacuum. You still can measure certain particles that come and hit you every now and again, you know, and get caught in your instrument. And so you can measure the density, you know, the amount of particles you see with these types of instruments. And you know, many of these same type of in situ instruments that I'm going to show you, I'm going to demonstrate some of this data here. These instruments are on Parker Solar Probe, for example. They're critical to Parker Solar Probe. As a matter of fact, you know, Justin Casper, who was at the Senate hearing just recently and did a fantastic job talking about space weather and the Carrington event. He is the PI, the principal investigator, on one of these instruments, so these in situ instruments. So it's really critical that we have them, and we have a savvy science team that can build them and ensure that they're going to work in some of these hostile environments. Because without them, we can't see these structures. We have a lot harder time envisioning what they are, especially from things like the inside out, because the white light stuff can only tell you so much. Okay, so what you're looking at, if I can do this here, so you're looking at the core, that thing, that flux rope thing that's colored and shaded in tan, that's the core. And we call that the flux rope core typically. Now you also have, if I can point in the right place, you also have blue magnetic field, I think that's blue colored. These are magnetic field lines that are draping around that structure. Remember, the solar wind has magnetic field all the way through it, has magnetic and electric fields all the time. And these fields, at least the magnetic field, gets draped. The stuff in front of it, it's just like water. If you're trying to push through the water, the slower water kind of drags around and becomes almost like a wake or something, let's say around a boat or something like that. It's very similar here. You have magnetic field that's still, believe it or not, attached to the sun at one end. But if you've got something trying to plow through it, well, it kind of distorts that magnetic field and drapes it around, almost like a curtain, around your obstacle, around that structure. So inside most ICMEs, and I'm calling it an ICME because now we've moved from the sun, where you call it a coronal mass ejection, to interplanetary space. I stands for interplanetary. So now it's an interplanetary coronal mass ejection, or ICME, as opposed to a CME. And as you can see, as we talk about the different kind of data that support it, now you see why I have to talk about it that way. You have to separate CME from ICME because even though we all know they're kind of the same structure, oftentimes the observations of the structures are so different. You have a hard time, even as scientists, we have a hard time intermingling the two. And that's a big problem with stealth CMEs, which I won't go into at all, because that's a totally different topic. But that's one of the things that Nariaki, Halo CME, and I are doing, and we're actually going to be at the ICME meeting in Bern here in a couple weeks, getting back together with the team, trying to understand those elusive structures. So we've got this envelope of, I'm trying to move this way, envelope of magnetic field around this internal core, what I often call the core of the solar storm, which is the flux rope. You also have a shock on the outside of it. I'm drawing way too big. Sorry, you have to deal with me, guys. I'm learning. There's a shock that kind of goes, see that outside? It says shock, and it's got this pretty single line that goes up on the outside of that. That shock, that's the shock I'm talking about that actually can drive radiation storms. Now, when we look at the data, and don't let it scare you, it's really not that big a deal. We have, you can see 1, 2, 3, 4 panels in this simple diagram. I know it doesn't look simple, it looks pretty ratty, but don't let it scare you. Okay, we're looking at 4 different things. The magnetic field strength in that top panel. The 2 really ratty panels are really the direction of the field, which is most of the time, it looks like nuts, it's messy. It gets cleaner inside of these coherent structures, but most of the time in the solar wind it looks pretty ratty. And then the bottom, we're looking at velocity. We're looking at the speed of this structure. Okay. Now, how you read the plot, for those of you who are not familiar with solar wind data, how you read the plot is in time. Let me put my hand up where you can see it. Down here. Okay. Down at the bottom, you can see date in August 2014. That's because that's the example we're using. It goes from left earlier in time to right later in time. Okay. So you're looking at data that starts, I forget what day it starts. Looks like the 15th of August, is that right? And it goes to, looks like the oh gosh, is that the 25th? Yeah, to the 25th. So that's 10 days worth of data right there. Yeah. Does that make sense? Yeah, because then you've got a CME that's a big CME. This CME, as you can see, lasts a couple days, and that's pretty big. Typically, a coronal mass, or an ICME will last about 24 hours-ish. They've got to be about that big. But we are seeing, especially in these slow cycles, we're seeing smaller and smaller ones. But the classic definition of an ICME would be it has enhanced field, and you can see it right there. See it between those two red lines. If you go up to the magnetic field up here, you can see that big bubble, right? That big bubble, that is the magnetic field of this coronal mass ejection. Now, what you also see in the next plot, you see kind of a field line that goes whoop, and then it drops, and then another line that comes down below it, and it goes up. I'm butchering this terribly. I'm so sorry. I can't point to it on a TV. I have to look on a screen. So you see a line that goes up here, and then down here. Am I too far? Yeah, too far. This line here. There we go. This line, it comes back up. What that is, you're looking at an angle. And this is why I don't like looking at magnetic field components using angles, is because it'll disappear up the top of one screen because it goes up to 360 or 180, and then it comes back down and starts over. So it looks very disconcerting. But it actually is a very smooth rotation. You can actually see another smooth rotation. This is also an angle. If I get to the CME, and you can see it go up and then back down again. See how it goes up and then back down? There. That is another rotation. And these are the types of rotations that you see when you have slinkies. In the core of the solar storm, that's where you will find these types of rotations. But, as you can imagine, when you look at a structure like this, do you think your spacecraft will always pass right through the core of the structure? Right? Or will it pass through the side, like I showed? That's too far. Here's the side, I think. Yes. Here's the core. Right? So you could try, this whole slinky could either pass through you. If you're a spacecraft sitting here, the thing as it goes out could either pass through you and you see the slinky, or if you're a little bit further off to the side, as the structure passes you, all you see is what we call the envelope. And now all you see is kind of ratty field. You don't see this pretty structure that you see here. You see, kind of maybe the stuff in front where it calls, see this says sheath up there? That's a lot of times what you'll see, but you won't see anything pretty. You might see the shock here here it is. You might see the shock here as you pass through it, because you can still pass the shock. The shock extends much further out than does the actual core of the solar storm. But you won't see anything coherent behind it. And that begins to cause problems for those of us in the science field. Here's a paper done by Thomas Zurbuchen and Ian Richardson. It's a very wonderful review paper. You might recognize the name Thomas Zurbuchen because he is now the Associate Administrator of the Science Mission Directorate at NASA. He is a heliophysicist, just like I am, and a good friend, a really good colleague, and a space weather advocate. So we're so happy to have him filling that slot. But he and Ian did a beautiful, and Ian, by the way, is also on the ICI team. So Ian is a solar wind guru, and we all adore him because he and Hillary Kane have done more work for this field and made more advances in ICME physics than maybe in any other two people we can think of. We still use their lists to this day to be able to look at ICMEs and know where they are and where they've been in history, how many times we've seen them, and do amazing statistics with their lists. So we're very grateful to have them as colleagues, and I'm honored that he's my friend. At any rate, this paper is amazing because it talks about ICMEs, all the different ways you can identify them. And as I stand on this side now, these are all the different ways. This is one of the tables in here, and I can't even count. I'm going to look down here for a second. I can't even count, but I'll tell you. It says, you may not be able to read it, but you might. Rotation, enhancement, variance, decrease, discontinuity at the ICME boundaries, field line draping around the ICME. Remember we were talking about the draping of that stuff, the envelope? Right. They talk about magnetic clouds. We talk about declining velocity profiles, extreme density decreases, proton temperature decreases, electron temperature, upstream shock signatures, enhanced proton ratios, oxygen charge states, unusually high iron charge states, occurrence of helium, enhancement in the Fe, the iron-oxygen ratio, unusually high different isotopes of helium, ion acoustic waves, bidirectional electron straw, bidirectional electrons, period, and ions, you can get ions as well, cosmic ray depletions, and bidirectional cosmic rays. Yikes. We have so much instrumentation that measures all sorts of different things in the solar wind that allow us to identify all sorts of things in these ICMEs that make them unique. The problem is, none of them line up. The problem is, they're not always there. Sometimes some are there, sometimes others are there. And there has been decades of work arguing back and forth what are the definitive markers to identify an interplanetary coronal mass ejection. And I don't think the debate is completely settled. I think most people at this point now believe the more markers, the better. But it still takes pretty much a scientist in the loop to be able to definitively say, is that an ICME or is it not? And there are definitely times in which people disagree, because there are, as we'll see, the solar wind can mask a lot of these properties very, very easily and fake us out. So let me show you just a couple things of what I'm talking about. So again, this may horrify you, but don't worry, I'll walk you through it. And I'm not going to take too much time. Here's 3 different types of ICMEs, and this is going to be a little problematic. Maybe I'll even do this. I'm going to keep my little cheat sheet with me. It's my little iPad. You can take a look and see what I'm doing here. So now I can actually see what I'm talking about while I point at it. So here on this side, you're looking at pretty much the same kind of ICME that you saw before. This is what we call a magnetic cloud. It's where the solar slinky is so much the bulk of the structure. It's perfect. It's beautiful. I mean, it's like the CoverGirl model of interplanetary coronal mass ejections. You can see that beautiful rise and I guess this isn't quite as pretty as I thought, but you can see the beautiful rise and fall of the structure and of the magnetic field in that structure. And as we look at some of the rotations, you can see the second panel. You can see that rotation slowly going up. If I get my hand out of the way, I'll try to point and pull my finger down. Come on, right there. That panel right there. You can see in between those 2 purple lines, you can see that line going slightly from below that gray line, which is 0, to above that gray line, which is a positive. That is showing a rotation, and the panels are really squished, so you don't see how pretty that rotation is. But it's actually quite nice. And then we also have, I'm going to skip down another panel to this one where it shows gray. So you see right there that the area that's colored gray, that's showing you that there's a depression in the temperature. Cold temperatures are often a sign of these structures, especially in the core of the slinky. Inside these structures, it can be very cold. And prior to this current cycle, we actually, that was one of the definitive markers. When we had much larger solar cycles, we had many more beautiful magnetic clouds, and they were much colder. There's a lot of reasons for that, which I won't go into. But then, let's see, then you can see I'm going to come down here to the velocity profile, which is up, there you go. That's a velocity right there. You can see it slightly declines, kind of dips down just a little bit. That's classic deceleration of an ICME as it goes out in the solar wind. And then there's all these other markers. A lot of these are iron charge states and oxygen ratios and stuff like that. The heavy ion concentrations, and those can be all over the place, but they have to be elevated to some degree. And I won't go into that because that's a little bit beyond the scope of this. But if we switch to a different kind of structure, look at this one. Look at this next one, the center panel. Would you look at that in the magnetic field and say that looks like an ICME? Actually, let me stand on this side so you can compare it to the beautiful one. Does that look anything convincing that there's anything there? And yet, look at the incredibly cold, look at the gray, the incredibly cold temperature we've got. Where is that thing? Right here. Look at that incredibly cold temperature we have. Okay, that is definitely an ICME, but harder to tell. And we also have different signatures up above. Those are bidirectional streaming, or directional streaming, electron straw. And so we can look how radically different those signatures are as well. And in this center one, this center example, we actually have bidirectional streaming. You can actually see it inside. There's a red spot on the bottom and a red spot on top. I'm not going to go into that too much, but it shows that that is a marker that this is an ICME, even though the magnetic field doesn't look like it is. And then this last one, there's all sorts of stuff going on. You see an enhancement in the field, and then you see it die down. You see the temperatures dropping. You see rotations, not as clean, but you see them. There's also, so these are 3 different examples, let me put this back, of interplanetary coronal mass ejections. And they have to be seen and viewed by using different markers, because we can't always tell. Here's another example, and I should be able to back out of the way so you can see this. Here's an ICME with what we call a magnetic cloud signature. That magnetic cloud is that flux rope. It's that solar slinky, but it's the most beautiful of solar slinkies. Magnetic cloud was defined by Len Berlanga back in, I think it was 1981 or 1980. It was one of his seminal papers on what magnetic cloud signatures, in which he actually defined what such a structure was. At the time, it was defined that it had to be a rotation in the magnetic field, which you can see up at the top panels here. That rotation had to last over a day, because at the time we were worried about sector structure, magnetic sector structure, and people didn't want to get them confused with crossing a sector boundary, which also has a rotation in it. But Len was very careful, so he said they have to be larger than 1 day, or about the rotation on the length of a day, in order for them to be considered magnetic clouds. And you can see some of the other signatures here that are very, very beautiful, and they all line up pretty much with the magnetic field rotation, and it's just wonderful. It's like the picture-perfect definition of what an ICME should be. But then you go to the other panel, and what are you looking at, right? It's hard to say. You get some indicators, you get cold temperatures. In this case, you get a declining speed profile. You get enhancements at the tail end of the structure, but it could leave some people scratching their heads. So ICMEs that are flux ropes are much easier to define and much easier to predict. ICMEs that don't have that, well, you're probably not passing through the core of the structure. You're probably passing through the envelope, and it's anybody's guess what you're going to get. It's like Forrest Gump's box of chocolates, okay? Luckily, we are not scientists in this group. We are space enthusiasts. We are space weather, watchers. We need actionable things. We don't have to solve all the academic problems. We only need to concern ourselves with identifying magnetic structure, essentially, of these structures of these things, simply because that's what we predict at Earth. That's what ends up being the driver of whether or not a solar storm, as it hits us, is going to actually cause aurora, cause disruptions for your ham radio and shortwave, cause issues for satellite operations, cause GPS errors, or not, right? Now, the intensity matters when it comes to density and velocity, speed of the structure, that matters. Density of the structure, that matters too. But the thing that matters the most, and the thing that we actually have a chance of predicting when we pass through the core of these structures, is the magnetic field. And I'm going to show you a little bit of how to do that. Now, I don't usually like showing stuff from my own papers, but I actually am doing that this time. This was some of my graduate work, and I'll show another version of this shortly. But if you take nothing else away from this course, this is what I want you guys to take away. If you learn about these structures as slinkies, okay, then it's very easy to translate a slinky idea into a flux rope idea, okay? What you're looking at in these 4 panels, before I get too far into it, what you're looking at is what we defined as magnetic cloud type. You're seeing essentially a slinky, okay, that's kind of like this, that is threaded through the middle, right down the pipe of this structure, with a magnetic field that's an axial, what we call an axial field. Like stick a broom handle through this thing and have it point this direction, or stick a broom handle this way and have it point this way. That is what a flux rope is. And really what it means when you fly through it is that the magnet, when you first fly through it, you're going to see magnetic field that is turning in a particular direction, right? It's going to be it's helical, so it's kind of spinning around like a slinky. But as you move through to the center of this structure, you're actually going to see field that is pointing this. If this thing is sitting like this, you're going to see the field pointing this way, or you're going to see the field pointing this way. Hopefully that makes sense. So as you hit the front end of this slinky, you'll see magnetic field that points either this way or up, right? Or if it's the other way around, it's rotating this way, you'll see it pointing this way. Either way, you're going to see field that's either going down or up. And as you penetrate through the inside of this structure, you're going to see the magnetic field, what we call the axial field, that goes through the center of that structure. And that's going to be like the direction of a broom handle pointing either this way or this way. And then as you fly through the back of that structure, then the field becomes more helical again. And it's going to either be pointing this way or this way again. So as this structure flies over you, the magnetic field you'll see will rotate. It will smoothly rotate. And you can actually, assuming that this structure is well formed, that it's not all distorted and twisted and stuff, you can actually predict what kind of field you're going to see. And that's what these things are all about. Let's see if I can stand far enough over here to get out of the way. Yes, kind of. Okay. So if we think of a compass, if we think of north, and what I may end up doing, oh, I'm out of focus now. I want to make sure I don't lose that. Let me do this. I'm going to put my slinky down, and I'm going to pick this up again, because I need to look this way. I'll just set it over here for the moment. Excuse me. Okay, let's talk about this one from this side. Okay. If we, with our slinky, if we think of a compass, okay, and in this case, the compass is going to have a north field pointing north, like pointing up. South is going to point straight down. In this case, however, west is going to point this way, and east is going to point this way. Okay? That compass, we can use that compass and those definitions of field directions at the different points in this slinky to be able to indicate what it is we're seeing and what kind of solar slinky we're looking at. For example, if you look at this one, if I'm pointing to it correctly, this guy right here, okay? Hopefully you can see the arrows, okay? So that's a slinky that lays what we call in the ecliptic plane. It's low inclination like this. It's laying flat, okay? This slinky has field that is down, points south when you first hit it, when it first hits you, right? As you go to the inside of that slinky, now you're going to look at the axial field, okay? And in this case, no, the axial field is pointing this direction, east. Okay, I'm going to move my hand. So you see leading field down here. Come on, leading field right here. See it south? Okay, and then you have an axial field that's going to be pointing east. Okay, that's the center of the slinky. And then when you get to the outside of it, now that field is pointing the opposite direction. It's helical again, so now it's pointing back north. And if you look at the trailing field in this plot, here, it says north. Now just looking at that alone allows you to say, okay, south, east, north. And it gives you this configuration for the solar slinky. And if anybody knows the right-hand rule, well, you know that this would be right-handed this way, but that's not what this thing's saying. It has to be left-handed. So you know if you talk about helicity, that just means which handedness is it. You actually will get a left-handed rope that sits that direction. Does that make sense? I sure hope so. Now, it's easy because we'll redo this exercise again. Let's do the very next one, a southwest-north flux rope. Okay? Now, again, we've got the same kind of low-lying flux rope kind of sitting here. But now, the field still goes south in the front, and it still wraps around and goes north in the back. But in the middle this time, our broom handle's pointing this way. So when you hit it first, it's south, you go to the middle, it's pointing west, and then you go up, it's pointing north, okay? Remember, west is this way, our nomenclature, and there's a reason for that. But west points this way. It's not the same as a compass on the ground, okay? So east is that way, west is this way. And you'll see that when we talk about the solar wind. So then, let's talk about one more. How about a northeast-south? Let's say now, instead of the field going south in front, let's say it goes north in front. It points up. Well, that means that it will point south in the back, right? So the leading field will be north, the trailing field will be south, and in this case, our broom handle in the middle is still pointing east. So what does that mean? You get a north, south, or excuse me, north, east, south structure, okay? And on this side, I think it's northwest, south. So same thing, we've got a north in the front, we've got a south in the back, and this time the field is pointing that way, pointing west. So north in the front, or the leading field, west, axial field, south, trailing field. It's a northwest-south rope. So here's the cool thing. If you have these designations, imagine if you saw only partway into one of these slinkies, but you saw enough as you're flying through the core of this solar storm. You saw enough that you were able to classify it. Does that mean you could predict the rest of the structure? And when you guys see me do that on YouTube, when you see me put up on Twitter, I put these diagrams showing the solar wind thus far, and I say, over the next 6 or 12 hours, this is what the field is most likely going to do. And I always have to say most likely because a lot of times it doesn't, but there are many times when it has. And I say, okay, you guys can feel comfortable, you're going to have aurora for another 17 hours. Or I say, nope, guys, aurora is going to turn off in about 5 hours and it's not coming back. That's why. It's because I've recognized that we're passing through the core of the solar storm and it fits one of these categories. And so I feel comfortable enough to make a prediction. Now, this is what the structures look like for ropes that are lying like this. What about like this? Think we can do the same thing? Why not? Same thing. Now, I'll only go over one because it's basically the same idea. Let's talk about the west-northeast rope. So now, if you're like this, you got a slinky this way, okay? You now have a west, the helical field, the field on the outside. It is now spinning around this way. It's coming this way or this way, around you. It's not running north-south anymore. It's running east-west. So in this case, with this west-northeast rope, the field will point this direction, leading. So as soon as you hit this rope, you've got field that's pointing in this direction. In the middle, the axial field now points north or south, right? Inside this, you stick your broom handle inside it, it can only point north or it can only point south, one of the two. In this case, we're going to call it north. So this rope is going to have a northern field in the middle. And then when you exit it on the tail end, that helical field wraps back around, because it's a slinky, it wraps back around and now it's pointing east. So now you've got a west, north in the middle, north, east rope. And that's what you're looking at in that first panel. Okay? And again, you do your right hand rule or your left hand rule, whichever way you want to do it. You got a field that wraps around and you can see which way your thumb points. You know that's a right, that fits. I've got a west, a field that's rotating west. My thumb is pointing north, which is the direction that the field is pointing in the middle of the slinky. So this is a right-handed flux rope. If it's a west-south, let's see if I can find it, west-southeast, which is the last panel over here, the west has to be moving that way. My thumb points down, and that's south. East on the same way, that's a west-southeast. That's got to be a left-handed flux rope, which is exactly what you see in the helicity. So these rules are simple, really, right hand, left hand. And yet they work quite well when you have a solar storm that has a very well-defined core. It works really well with magnetic clouds especially. Now, for those of you who've wanted a simpler diagram that looks a little bit more like a slinky, here you go. Thank you, Erica and Amelia, for, as a matter of fact, you guys might remember Erica. She was one of the gals who did, from the ICI group, who did an aurora photo during one of my forecasts as a guest, as a cameo. She made this diagram, and it's a little bit simpler. Maybe I could have shown it to you first, but I wanted to kind of get the whole gist of it. So there's our slinky, right? You can see it there in all of these different diagrams, and that's our broom handle. See the arrow going through? And it's the same kind of thing. So there's a southeast north, a southwest north, northeast south, and northwest south. That's the low inclination stuff. And the high inclination stuff is the stuff where the slinky's pointing itself north-south. And so now all your field, your helical field, wraps east and west. So hopefully this gives you an idea. This is it. You think it's magic that I use to predict stuff. It really isn't magic. It's simply right hand, left hand, and solar slinkies. And that's about it. And now we will go ahead and try to do an example. Okay? So what I'm going to do, and this may be a little bit tough because I've got to get out of the way. It was a little bit easier with my TV, but let's see. Let me stand. I'm going to hold this thing over here. Let me put this up here. Okay. Sorry, I'll get better at this, but you guys got to let me know if this green screen thing is working for you. Okay, so back to the old diagram, and now we've got data. Oh boy, here it gets scary, right? Okay, so what we're looking at is solar wind data, and I'm giving you an easy one, and I'll annotate it in just a second so you can see what we're talking about. The top panel, if I'm pointing in the right place, yes, the top panel here, that is XBX, right? Don't worry about it. BX, that's the radial field. That's the field that comes toward Earth or away from Earth. That's used for something else that you don't really need to know right now. Once you get better at this, we can talk about that in an advanced class. But for all practical purposes, all you need to know about is the two components, BY and BZ. Okay, that's the BY is the east-west component, and the BZ is the north-south component, just like we had in the diagrams. Okay, so when you think, and I've even annotated it BY. I've even annotated it as positive or negative. So if you look at the second panel, we'll talk about BY first. Okay, now it's not very strong, but you do see in the middle between those two lines, which is inside, this is the core of the solar storm, you see a little dip that is a little bit below zero, right? You see the middle of that. It's not a strong rope, but this dip below zero is, anytime you go below zero, that is BY negative, right? It's less than zero. So you don't have to worry about it being positive or negative, just or how much it is. It's just, is it above zero or below zero in this case. So this is below zero, so this means that it is BY negative. So we know in the middle of this rope, if nothing else, we know that we're going to have a BY component that's negative. Okay, we'll have to go back to our thing here to see which might actually have a BY component that is negative. If we see a B plus component, we can just eliminate it immediately. So you can see right here, the very first one has a BY component that's positive. We can get rid of that in the axial field. And the third panel also has a BY that's positive, so we can get rid of that. So we don't have to worry about either rope, or this rope being an eastward pointing rope at all. It doesn't point east, it points west. West is BY negative, okay? Now let's take a look at the leading field. Let's look at the BZ, okay? In the BZ component, we see a strong field at the beginning, right at the beginning of this structure, right after that vertical line. That's where we've drawn the line where this flux rope starts. Okay, this is now entered the core of the solar storm, and we see a strong positive BZ. Okay, so that means north. A positive BZ is north. Okay, but look as you rotate through the center. Whoops, Let me get my fingers in the right place. Come on, fingers. Up here. There we go. Center of that rope, BZ goes to 0. So we don't really have a north or south component in the middle, which makes sense because we have a BY component. We have a westward component in the middle. At the trailing end of this thing, though, don't go too far there, we have a negative BZ. So the field goes from a positive BZ at the beginning of the rope, down here, to a negative BZ at the end of the rope. So it goes from north to south, okay? And the center component, the axial field, is west. So what we're looking for, when we annotate it, north, west, south. And that is that one. So that's what you're looking at, believe it or not. You're looking at a solar slinky that points low-lying in the ecliptic plane, basically laying flat in the plane where the Earth is, the Earth and the Sun. It's got a northward leading, it's got a southward trailing. Somehow we lost connection. Why did we lose connection? That was weird, we lost connection for a second. Hopefully that didn't lose too much. It said that we lost connection, so hopefully we're not down by too long. Let me double check. Where's my thing? Oh yeah, wow. Let's see. Are you guys still with me? Let me reload. Hold on. We have you now. Okay, good. I see people saying we have you now. Thank goodness. I got very nervous there. It lost about 15 seconds. Okay. Good. Just a couple seconds. Okay. It's 2 alternators at each end of the slinky. There was a time it appeared to buffer. Yeah, for some reason we lost connection. I'm not really sure why. Okay. Let me get through this and then we'll pause. Hopefully you guys saw this part. Let me go back to this. And push this on here. Hopefully you guys saw as far as getting to this section where you saw that we could actually predict this particular event. Now let me do one more really quickly. Hopefully we'll stay connected. Here's another one, but this one, this time, is for a high inclination structure, okay? Now, again, same kind of idea with the magnetic field. Let me set this up a little bit better here so I can see myself. Same kind of idea with the magnetic field. We've got BX, don't worry about BX, but in this case, we've got BY in this second panel here. And look, it looks totally different, right? Now it's the one with the leading field. And BY is positive at the beginning. Now if we go to BZ, the next panel, oh, sorry, I keep jumping too far, right there, down here, look at that. That BZ in the middle goes way south, but that's in the middle of the rope, you know, what we call the axial field. So that's a southward axial field. And then if we go back up to the BY, up at the trailing edge, now BY is negative, and that's west. So if we annotate again, we have an east, right here. Come on, back up. There you go. East, south, west rope. And if I back this up here so you can see, there you go. Look at that. So just that magnetic signature there tells us that we have a high inclination rope. So this thing is sticking up high in the sky, like this, out of what we call out of the ecliptic plane. And it's got a field that leads easterly direction, this way, but it's got a southward field in the middle, and then on the back side it wraps back around west, okay? And so if I do my right-hand rule, east, south, west, that means that this is a right-handed rope. And so we can get all of that information just from looking at the magnetic field components. And the cool thing about this is that if this structure were passing over us, passing over ACE or Discover, we would probably only have to get to about there, maybe a little bit further, right about here, not even halfway through it. And I would say, oh, I know what this is. And I draw the field lines and say, guys, I bet you're going to have aurora. If we're only about here, you guys are going to have aurora for another whole half of this cloud. And say, enjoy. You're going to have aurora going forever. Ham radio operators, tough it out because you got another 6 to 12 hours of, bad conditions. But you do get auroral propagation. GPS, don't fly your drones right now. Probably not for the next 12 hours. So that's one of the cool things about having structures that are very coherent. The sad thing is I just wish that these structures were, always looked like that. Here's an example where they don't. And I'm not going to kill myself because we've already gone over it so much. But we could actually, if I do it very quickly, for example, both of these ropes, you see them colored here. This is a very serious time series. It's got lots of junk in it, but I just covered part of it because you don't really need to see it. What you need to see are the magnetic field components. I will go ahead and do these very quickly if I can. I'll have to take a look. For the first event, let me see, back over here. Come on this way. It looks like it is, I'll have to look at it again. BZ is northward and in the center, but it's got a BY component that looks like it goes east. It goes west and then east. Okay, so this first orangey flux rope structure is an it's a west-northeast rope. Let me see if I got it right. Yep, there you go. And I'm going to try to stand out of the way. See if you can see that. Can you see that? So I'm not taking a lot of time with this. This is kind of an exercise left for the reader. And if we try again, okay, this next one. Now I'm looking at the blue rope, the blue structure, okay, and it in the Y component is positive up at the beginning, so that's east. The BZ field in the middle looks like it's south. That's this component here. There you go, south. And then the Y field at the end, the trailing field, come back over, there we go, is west. So it looks like an east-southwest rope. And now you see it there in blue. Okay, so what I gave you at first were the perfect versions. What I gave you here is an uglier version. Oftentimes we get structures that can be extremely complicated in practice. So just because I made it look easy doesn't mean it's always easy, not even for us. But it is possible when you get these structures in the solar wind, if you can identify the leading and trailing edge of these structures, you see that beautiful coherent rotation. There are other things that you can look for, variances and other things that go down just in the magnetic field itself or just in the plasma, like cold temperatures. These markers can help. They don't always solve everything. But once you get an idea of where the boundaries of that core, where that slinky is, then it makes it so much easier to identify. But that's assuming that you pass through the slinky. Sometimes you don't. Here's an example of a tough one. This is actually the model fits from that same example. And in one case, we actually had 4 spacecraft. We had Wind ACE, Stereo A, and Stereo B passing through 2 different flux ropes. And you saw 2 of the traces in that last plot. And it can get extremely complicated. And what I'm going to show is, you can see they're kind of both high inclination ropes, which is what I showed in the prior diagram. You saw that they were kind of sitting like this. And you can see it in that model. They definitely are. These little cans are sitting highly inclined. Now, the cans in this model are just the outline of these structures. It's not showing a helical slinky kind of thing. But it is showing that they're highly inclined. But you can have multiple spacecraft going through these structures and have it be extremely complicated. And I'll show you an example. Chris Mostel did a really great paper back in on the 2010 events that is incredibly complicated. The fact that he was actually able to pull it off is pretty amazing. And down here, and there's lots of different ways that we can fit these structures. This is just an example of a couple model fits that I did. And then down in the third panel here, you can actually see internal internally you can actually see the slinky. As we look kind of through the center of the slinky, you can actually see kind of the helical field in there, and that's Emilia's work that she did with some Grad Shafranoff stuff in one of her papers. Now, what you're looking at on the right-hand side, I mean the left-hand side rather, the reason why I put this up here, this is also part of the work that I had done with Ben Lynch and Alicia Reinert ages ago. What we were trying to do was understand really not just the ionic composition of these structures, but we were trying to understand the difference between the core and the envelope of the thing, and whether or not we could use our understanding of what the ionic composition, basically the heavy ions, what they looked like, and even the helium abundances, whether or not those things would be different in the envelope as opposed to the core, and we could be a little bit better about trying to understand how to use some of these identification markers to delineate where different parts of this structure is. And we had 4 spacecraft passing through a couple of these ropes, and again, that time series you saw was part of that. And really what you're looking at the top panel here are the tracks, if you're looking down from, let's say, on top of the solar slinkies. So the solar slinkies are sitting out like this now. Okay, so you're looking as if you were looking north, from the north down into them toward the south. And you're looking at those solar slinkies here and here. Now granted, they're oval, they're not round, and that's typical because you get a lot of distortion in the solar wind. And our models are idealized. The true distortion of these things is crazy, and I'll show you that in a second. But what you're seeing is kind of like a field pattern inside. You see some rotation and inside the actual structures. But you can also see that purple stuff. That purple stuff is actually the envelope, some of that draping field we were talking about before. And I want you to keep that in mind, because this is really what we fight as scientists. We fight looking at these structures from all of these different points of view with all of this jumbled stuff all around it. It's not just about the core of the slinky, it's about all of the stuff that goes with it. And as you look at the second, third, and fourth panels here in this diagram, what now you're looking at is a color coding of the ambient, the solar wind that these things are bathing in, that they're the bath and that they're having to travel through. And the colors, let's say, take velocity for instance, that's this VP panel. You can still see the outline of those magnetic field structures, those solar slinkies. But now what you've got on top of it is what the solar wind in and around these structures looks like. And the red is the fast wind, and the blue is the really slow wind. So look at this mess. They've got fast wind blowing at the top of them, slow wind down here keeping them kind of close together. Whoops. Where's my hand? Right here. Keeping them close together. You've got a fast wind stream behind them, right here, right? Whoops, right here. Come on, back up there. You got a fast wind stream right here. And all of this just distorts these structures, sometimes to a ridiculous amount. It makes it very, very difficult for us to even identify the cores in these things. If they have strong magnetic fields, they're strong slinkies, then they can survive and we can still see them. If they're weak, oh my gosh, they don't get shredded per se, but they can become unrecognizable when we look at them with spacecraft. Even the density, you can see NP, that's the density of the solar wind. You can see these plops of stuff kind of in between, these lumps of thicker, denser plasma that kind of cause issues. I mean, it's like jello, thicker jello to try to get through. So, and then we had temperature, that's down at the bottom. It's not as critical for what we're talking about. But I wanted to show you that the dynamics of the bath of solar wind that these structures are in can absolutely wreak havoc. And that's what I'm trying to talk about here. So what I'll show you really fast is a diagram of the Earth. I don't know if yeah, you got it. Diagram of the Earth right here with the Enlow model, and you're actually, the big tubes are not slinkies, but they're magnetic field lines. But the color coding is actually showing fast and slow solar wind streams. And so you can imagine if a big coronal mass ejection that has blown out of the solar wind is huge, well, it's going to be crossing through all of this solar wind. And very much like the panel I showed right before this, it's immersed in this bath of stuff that's just kind of swirling and trying to rip it apart, really, the whole time it's going out. And whether it's fast and it's driving through and plowing through this stuff like a big snowplow, or it's really slow and it's just kind of being carried out, you know. Either way, the forces on these structures as they're moving out into the solar wind are things that we don't really well understand yet, because we don't even understand the solar wind all that well yet. And they're so disparate, they're always changing, that it makes it extremely difficult to know whether or not one of these beautiful solar slinkies that we see emerging from the sun, if by the time it gets to Earth, it still looks as pretty as it did when it first was launched. Most of the time not. And a lot of times, these things can even rotate. Ben Lynch has done studies where he's watched these things blow out very, very slowly in like a coronal streamer blowout. One of his papers said the thing rotated something like 23 times. Could you imagine having a coronal mass ejection that looks like a pinwheel just spinning out? It boggles the mind. So we have a lot of problems when it comes to stuff like that, because how do you predict what orientation the slinky is going to hit Earth in? How do you do a decent magnetic field prediction for the intensity of that solar storm at Earth when you have no idea what part of this is actually going to end up being BZ south? Because the slinky won't stay still. That's the problem of science right now. And you can see examples of some of the runs that people have done. You can see here, this has an embedded solar wind. You can see the front end of that thing being squished. Sometimes it gets squished even more than that as these structures blow out. Here's another distortion. You can see how that the cone model of Enlil, these are numerical simulations, are really trying to show how incredibly chaotic and stochastic some of these processes can be, and how much they can distort these flux ropes as they go out. And then, of course, you don't just get one. You can get a whole complex of series, or a whole series of these structures, very complex series. Here's Chris Mostel's paper where he had a lot of people help him model all of these different eruptions that blew out all these different CMEs, and they were all seen at different spacecraft. So you can watch it from the sun and see very distinctly what the eruptions are. And then by the time they blow across the spacecraft, depending upon where the spacecraft are, even if they see the same structure, like the color coding of these cans here, you can see the sun and then you can see the color coding of the cans. The CME, the ICME shape is different. Its orientation is different, even though we know it's the same eruption. So, you know, you can have, and then the time series, of course, looks like this. How about do some prediction work on that in real time? Now, it's easy to, not easy, it's possible to do it from a forensics point of view, where you look at it as an academic project, and you spend weeks, if not months, on it. Sure, try to do this forecast in real time. I wouldn't. And that's part of the problem that we face with this field, is that we have incredibly complex stuff happening all the time. But we only have a few spacecraft scattered here and there. In this case, we had, what is it? We have Messenger, we have VEX, which is the spacecraft around Venus. We had Stereo A and B, right? That's it. Those are the only spacecraft we had. And they're all, one's at Mercury, one's at Venus, and then we had Stereo A and B that were just moving away from Earth or just gotten around, you know, on other, they weren't behind the sun yet. They were kind of just spread out in the heliosphere. So you can imagine, we've only got 4-point measurements trying to understand something that is easily the size, about a quarter of a distance from the sun to the Earth by the time it gets out to Earth's, you know, where it is at Earth. These structures are massive. I mean, they're just huge. And we only have 4 different spacecraft plowing through them at one point to try to understand what these things look like. And they're getting distorted and bent by the solar wind all the time. So you can imagine how incredibly hard that is to do. Okay, so before I go into the solar storm impacts, let me pause and see if you guys have questions. And then I'll try to get through this other stuff right away. Okay, so now we're going to start getting this weird mirror effect behind me. I hope that's okay. let's see, do you guys have questions for me right now? How do the X-rays make the sun flare? You got your causality wrong. The sun flares and then you get X-rays from that. Okay. Has she? Oh geez. Oh, we've got some fun. We got some fun stuff here. Any news from the Parker Solar Probe? No, not yet. Not yet. Honey. Oh, I know, guys. It's pretty funny. The Earth is flat. Yeah. Well, at least we know they're not going to be spacefaring because they won't ever leave it. So that's probably good. Okay. Do we have anything that's not a flat Earth question? Let's see. Yeah, thanks, Notani. I appreciate it. I need to make somebody a moderator to take people who just, don't want to learn anything other than what they think they already know. They can take that somewhere else. We are simply just trying to, I'm not even trying to teach you fundamental physics principles. If you want to go to an academic channel, go to an academic channel. All I'm simply trying to do is help people who actually use space weather on a daily basis get through their day, right? I mean, that's what courses like this are about. It's to learn enough about the phenomenology so that they don't have to go to graduate school, that they can sit here and learn enough that they can look at satellite data and say, okay, what's coming at me and does this make sense, so I can predict whether or not I'm going to go out aurora hunting tonight with my good camera or just my cell phone. Or maybe I shouldn't be flying my drone tonight because, I've got to deal with, and inspect that bridge that I really meant to inspect because there's going to be issues with GPS. These are the types of problems I'm trying to solve. So, if you want to talk electric universe and all that kind of stuff, go to the Electric Universe channel. And you can talk academia all you want. But right now, these courses are meant for people who live and breathe space weather because they need to. And so I appreciate questions like that, not questions about flat Earth and how electric fields drive all solar activity and stuff like that I wouldn't even want to address on a good day. Let me ask you guys this, because I don't see any new stuff in the chat. Do you guys understand the slinky stuff and prediction well enough? Because I'm going to get into some of the solar storm stuff, and I just want to make sure that you guys understand all of that stuff well enough to be able to move on. Let's see. It sounds like we need more points of reference out in space to get a more complete Yes, absolutely. That is part of the issue. Thanks, John, by the way. I appreciate you saying that. That is part of the big issue. That's one of the reasons why Nariaki oftentimes will talk about trying to get multiple probes kind of in like every 60 degrees around the Sun-Earth line, in Earth orbit, but all the way around. He talks about that because to be able to have those monitors in the ecliptic plane will at least allow us to get a little bit better understanding of these structures. The biggest problem that we have right now, though, in our field, is that what we really need are monitors, satellites that are monitoring the sun out of what we call the ecliptic plane. There's the plane that all the planets sit in, and that plane is really, it's very energetically easy for us to fly satellites in and spacecraft in. Where it gets to be difficult is if you want to get something up out of that ecliptic plane and at higher latitudes. So something, a polar orbiter, let's say that's orbiting the sun this way like Ulysses did, for example. Those types of missions are extremely useful because they give us views of the sun that we don't have and that we desperately need. We can't view the North Pole of the sun very well or the South Pole of the sun very well right now because we're looking at it from the side, right? You look up at the North Pole, you don't see really what's going on from the top down, or the South Pole from the bottom up. We really need to see that stuff so that we can get a better idea of what the sun's magnetic field is doing. Without it, we kind of have to take really rough guesses, and our measurements don't do so well. So all of our models are off, and we know that. And it really is because we can't get the north and the south done very well. So those are the types of missions that we really do need to fly as well, and those are probably more important. But because they're more energetically tough and technologically tough, those missions are far more expensive. And so we probably won't be seeing anything like that unless we end up getting a lot of public support. You know, we need to have a lot of people out here who are saying, look, we need this stuff to do space weather predictions accurately. And because of the way our technology is growing, and because we have people that are working in space, and we have a lot more going on than we ever used to, where these satellites are critical, we need to be able to do space weather the right way. And as space weather continues to grow as a field, it will become that much more evident why we need to fly some of these really expensive missions, simply because we can't do space weather otherwise. Okay, maybe my chat died, so I'm taking a cosmos physics course right now, and we're on the sun. This class just helped me tremendously. Oh, that's great. I discovered your class because I'm SWL, so plan to follow you. Thank you so much. Please check out some of my other classes. This is a good place for me to mention to you, by the way, that I am going to be, I'm going to eventually be taking the live courses off of YouTube, the ones that are already archived there. They will always be available to Patreon members, but I'm going to take them off the channel so that I can cut them down and make them a bit more sizable. So like little stops and starts like this, where I'm addressing questions or just discussing things that may not be completely relevant to the course. I'll cut that stuff out so that I can make the course a little bit shorter, because I think the last course ran incredibly long, and I don't want to do that to you guys. So expect those courses to be kind of shuffled around, and if you want to take a look at some of the mini courses or download them that are still up on the web, do so soon, because I will be coming down. Except for you Patreon members, you guys will always have access to them. Okay, let's see. So now I'm getting a lot of questions. Wow. Very much like basic electronic hand rule. It's exactly right. We use this all the time. Your right hand, left hand. I used to be made fun of when I was a graduate student because I'd be going around like this all the time, and because I'd have to be thinking about flux ropes on the fly. So I was always giving people thumbs up, and they were looking at me strangely. But yes, we use left hand, right hand rule all the time. Relation between CME periodicity and solar flux index. I would absolutely say any relation you find is coincidental. Yes, there will be some kind of relationship, because the solar flux index oftentimes will boost when you get a bad actor, meaning a sunspot that's very unstable. A sunspot that's very unstable on the sun, not only does it emit a lot of in the electromagnetic spectrum, so you will get your solar flux to increase, but it also will be shooting off solar flares and coronal mass ejections all the time. So yes, there will be a correlation, but that could accidentally lead you to think that there's a causality correlation in there, and that's not necessarily true, because coronal mass ejections can erupt without big sunspots on the sun. So really what you're looking more for is solar flux. If you're looking at solar flux relationship, you're going to be looking at it more for active regions and really the plage regions of the sun, and the areas that are actually around the sunspot, not the sunspot themselves, but the bright regions around it, because that's really where the emissions come from. I have a course on that, by the way. I think it's sunspots and telescopes, and I talk about that. Let's see. Are the solar storm arrival prediction times in the UTC time zone? Yes, they are. You will always see people use the UTC time zone because it's a global time zone that allows us to keep everything consistent. So yeah, always think UTC. All right, thank you for being on Ham Nation. Oh, you're welcome. You're very welcome. Does sunburst only equatorial, or is it also the poles? The sun will burst both. Typically near solar minimum, or as the sun begins to quiet down, you will see more equatorial bursts, but during solar maximum, the sun is really what we call multipolar, and so you will see coronal mass ejections lifting off from very high latitudes, and it can be they can be very spectacular eruptions, not just soft, the gentle stuff that lifts off the sun, but really explosive. So during solar maximum, you expect to see more coronal mass ejections launched at all sorts of different latitudes, and then as things calm down, then more and more of the eruptions become lower and lower latitude. Kind of like sunspots do too. When you cut out the extra stuff, please do post them together as a general question presentation. Oh, that's a great idea. That's a great idea. Thank you. Right, will do. Okay. I appreciate that. Tim Rogers, thank you for that. So CME periodicity increases during the solar cycle as it climbs. As the solar cycle climbs, as the activity increases, absolutely. Yes, you get more, all different types of eruptions as the activity increases. You get both eruptions from these bad actors, because you get more sunspots on the sun, and a lot of them are very unstable. So they will be flare active and launching coronal mass ejections all the time. And then, of course, you also just get a more unstable upper atmosphere in the sun, with the sun itself, just because of the activity it is and the fact that its magnetic fields are changing. That's actually when the poles are flipping, is solar maximum. So it's really, the sun turns kind of like a lava lamp at that time, because you actually have islands of different magnetic polarity all throughout the sun. It's very bizarre. And so the solar atmosphere is very unstable, and it's reconfiguring all the time. So you can get ejections just lifting off even without sunspots, even lifting off in the what we call the coronal streamer belt. You get them lifting off without it being sunspot related. How does solar flux ionize the atmosphere, or the ionosphere? That I'm not going to go into. It's more chemistry, and I will probably talk about that when I get a course up on ionosphere and radio propagation and stuff like that. But that's a great question, so hang on to it. Oh, for him, oh good, for you DXers, these presentations are excellent. Thank you. I'm sorry they go so long. Okay, so looks like I've got it down pretty well. Looks like you guys are, for the most part, understanding this stuff. Please feel free to review it or ask me questions. If you go through it, the exercises yourself, a little bit more slowly, or pause the presentation before I give you the answer, that should probably help you. And remember, it's not every ICME that you can do this with. It's only with the core. When you pass through the core of these ICMEs and it's clear that these things are flux ropes, that's when you can actually do the prediction. So okay, so now let me get back to the presentation, and let's talk about solar storm impacts. Okay, so what are typical solar storm impacts? And these are the people that I care about. Oh, let me plug in my, hold on. Okay. Are we still working? Hold on. Okay, good. Sorry, my thing froze for a second. Okay, so what are typical solar storm impacts? Not very much, right? Just these little things. Satellites, communications, airline transportation, national electric utilities and power grids, location-based services with GPS and GNSS, people who use Waze, people who use, oops, pardon, I'm out of focus again. People who use Waze, people who use Uber, Lyft, those types of things. We have, of course, satellite wireless and mobile technologies, satellite radio and TV. The Internet of Things is becoming a bigger deal. Of course, emergency and disaster prep, rescue and relief services, search and rescue operations, everything to do with drones, and that's part of the emergency and disaster and rescue stuff, as well as people who are doing Aurora tourism and delivering packages for Amazon.com. I mean, there's just a whole host of them. And of course, we have space tourism and Martian colonization. Those things are coming up as emerging markets right now, and it's going to become even more critical to us as time goes on. And O3b, we've got who is it that just launched some satellites into MEO orbit? They're going to be noticing very quickly that that their satellites need to be radiation hard when the sun starts getting very active again. We could be seeing a lot of outages with the OneWeb, right? They're lighting up satellites. They may be in low Earth orbit, but I know O3b is doing MEO orbit. But even the OneWeb satellites, they're going to be dealing with satellite drag when we have big solar storms, which causes the satellites to change orbit, believe it or not. And it can be really problematic for LEO orbits or LEO satellites. So there's all sorts of things. And you guys are the ones that I teach these classes for, is that you're dealing with these types of issues every day. So let's talk a little bit about, not just a normal solar slinky, but let's talk about a super solar slinky. Right, I've got some stuff that I could show you about the normal stuff, but let's get into the real fun stuff. What can a super solar storm level event do? And back on March 6th, 6th through 15th, back in 1989, we had an event that we call the Standard Candle. And this was not only a flare event, they had a very large solar flare that occurred, but we also, I think it was like an X32, it was something pretty outrageous. But we also had a big solar storm afterwards. Now, when the solar storm hit, and I think most of these are about that whole solar storm, this is when the actual coronal mass ejection hit. We had weather satellites that lost images for hours. The TDRS-1 ComSat, this is a military ComSat, it had over 250 anomalies while in orbit, so it couldn't do its job. So the Space Shuttle Discovery, its fuel sensor failed. The Radio Free Europe, this is a radio station. Remember, this is back in 1989, so it was disrupted, and it thought it was a Soviet jam event, because we still had the big Red Scare at the time. Now, the Hydro-Quebec power grid also shut down, and the James Bay network, which served over 6 million people, was offline for 9 hours. This caused the Toronto Stock Exchange to close. Now, imagine back in 1989, we didn't even have smartphones. I'm not sure how many people even knew what GPS stood for at the time. And nobody had an idea. Nobody had an idea what space weather was, right? Space weather was a joke. It was, an academic field. It wasn't something real. So how in the world can you worry about space weather causing something like closing the Toronto Stock Exchange down? You don't. You don't worry about that stuff. And the funny thing is, I met a guy just recently, just a couple years ago at Hamvention. And he came up to me after I gave a talk and I presented this slide, and he said, oh my God. He said, I was a little kid and I lived through that event. And I said, you're kidding me. He said, I'm now 40-something. He says, I've never known what caused it. He said, none of my family knew. He said, everything went out. The power went out. Everything went out. We had no idea, and nobody ever explained it to us. When everything finally came back on, nobody had any clue. He said, it's taken me 40 years, and you presenting that information to me, what's here, for me to even have a clue what happened. He said, thank you. This has been a 40-year-long question for me. And I just kind of smiled and laughed that, wow, us scientists, we knew what was happening. But the general public, no, they didn't know. Wow, why is my thing dying? Why is this not charging? Hold on. Is it charging or is it not charging? My adapter suddenly is acting like it's not charging. And it says it's going to die here in a second if I don't. I hope, if I go offline, guys, it's because this thing's not able to charge for some reason. Hold on a second. Yeah, it's saying 5% and it's not charging. So let me figure out what is going on. Are you charging? It's saying it's not charging. I don't know, guys. So if I go offline, I'll have to figure out how to get back online. My iPad is not charging, and it's running this whole show. What in the world has happened here? I don't know. Huh. Let me see if I can get a different adapter. Hold on a second. Do I have a different adapter? Is it still going? Yeah, it's still going. Let's see. I don't know if I have a different adapter I can use. This one may have to, if I turn this off, it may not charge either. Shoot. I don't know, guys. I may have to sign off here. That sucks because I've got still half a class to present. So I can't tell if it's charging or not. And I'm not sure why it wouldn't be charging. Let me try this one more time. Hold on. Sorry for this. Yeah, it looks like my poor iPad is going to die. So we may I may have to continue this course at a different time, guys. I'm so sorry for this. I have no idea what's happening, but I will. If it dies, then we will just continue this in a little bit. So I will just reschedule it for you and finish the rest of it. So what I wanted to show you just from this really quickly is, let me stand on this side now. Here's an example really fast of what that nasty storm did back in 1989. It killed, you could actually see some of the dark regions in this nighttime picture. These are the city lights as viewed from a satellite. And you can see the dark regions, and those are regions where there was no power. And you can see the transformers off to the very far left here. Those transformers were melted, right? And this is what everybody's worried about with the big Lloyds of London report and Obama's administration putting out the big, the big solar storm report of the Carrington event. They're worried about this stuff because it has happened in the past. And here's a satellite. This was a DoD weather satellite. Now this satellite was made to look at weather in the daytime. And here it is looking at aurora at night. And you see that white band that's completely saturated. That's aurora. And it's completely saturated this instrument that was intended to be seen during the day. That's how incredibly bright this aurora was. So we had aurora that was viewed, I think, clear down to Texas. Down to Texas and Florida. I guarantee you, if we had had social media, we would have had aurora seen much further south than that. Because with the advent of social media, we're able to catch this stuff right away. We can alert people when there are intensifications, all that kind of stuff. And so aurora was probably visible much further south than even Texas and Florida. Some of the smaller storms we've had people who have seen aurora down in Arkansas, down in Payson, Arizona. They've seen it very, very far south, even Oklahoma. And the storms weren't nearly as intense as what you see here. So I guarantee you aurora for this particular storm was seen far further south. But this event, if you guys watch the Senate hearing or anything else, this is the event that is the benchmark event for national grids. These are the ones where they set all the information about what is a storm that they have to survive through. It's all been found from this data because this is one of the superstorms that has happened in the modern era. Now, it's not the only one. We've had others, but that's the one that we use. Now, it's not a Carrington class event, but it's a strong event that is actually doable. Now, if we go to a more intense event like the Carrington class event, we couldn't survive that. I don't think any of the power grids could survive it. I think with the 1989 event, something like I'm trying to remember, I think they've got 7 volts per minute in their power grids is what they can withstand. And a Carrington class event is hundreds of volts per minute. The power swings are insane. And nobody can live. That's sometimes an order of magnitude higher than what any power grid, even at their extreme levels, can survive. So really trying to get these guys to live through a Carrington class event is very, very very difficult, especially without help. This is why I think the public can actually help. But we can talk about that later. And I'm still worried this thing's going to crater on me. So if I accidentally die because my iPad's not charging, forgive me, and we will start this up again. But now let's talk a little bit about the Carrington level superstorm. It was actually a series of events, just typically like everything else with the sun. When you have a bad actor on the sun, it will fire off a flare, and then it'll fire off a solar storm, and it's still angry, so it fires off another flare and a radiation storm and another solar storm, and it just keeps firing, bam, 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 all the way it rotates from the east limb of the sun to the west limb of the sun. It won't stop. And so, unfortunately, that means that space weather events come in a series, typically. And it was no different with the Carrington event. It wasn't a single event. It was actually multiple events. The one that everybody remembers, of course, was the September 2nd event, but there were multiple ones. Now, this was the first ever recorded solar flare that resulted in a massive solar storm. It was observed, and I'm standing in front of it. Carrington actually was one of two solar physicists, or astronomers rather, solar astronomers, that actually could see the ribbons of the flare occurring, and that was the picture he drew. It was a white light flare. Most flares you can't see with your eyes down here on the ground because the atmosphere absorbs all of that gamma ray, X-ray, EUV radiation. So even with instruments on the ground, you can't see it. You have to go up in space typically to see it. But this time, it was a white light flare, which are reasonably rare, and Carrington was able to draw it. So that's how powerful this flare was that it let off so much energy that you could actually see it in white light. That's pretty intense. So it was the largest in the last 500 years, 3 times larger than the March 1989 event. So you can imagine, that March 1989 event you saw that tanked all those transformers, that kept people, that closed the Toronto Stock Exchange. This was even bigger than that by at least 3 times. The North American telegraph system failed. I'm sure you've heard stories about how we had hundreds and hundreds of miles of unbroken line, and what happened is because of that, with the Earth wiggling, the Earth's magnetic field wiggling so much, it induces currents not in the wires themselves, but into the ground. Believe it or not, a lot of our ground rock is conductive, and so that induced the currents that were induced into the ground, then induced currents back up into the wires. And it's not that it induced all that much current. The currents weren't very strong, but it's just that we had so many hundreds of miles of unbroken line, and it's incremental. So a little bit of current plus a little bit of current plus a little bit of current plus a little bit and a little bit and a little bit, and eventually it became big current, big potentials, big current, and that current traveled through these wires right into the telegraph systems. The telegraph machines, people were unplugging them and they still were working because they didn't need electricity from the wall anymore. They were getting enough electricity right through the telegraph wires themselves to continue functioning. And the problem was that there was so much overload coming from them that the machines began to spark, and they caught the telegraph paper on fire, and it would burn their operators and all that kind of stuff. So that's how you hear about fires. It's not that buildings are going to spark to the point where they burn down. It's just that in this case, that's what happened with the telegraph paper catching on fire. The aurora, of course, was so bright that animals thought it was sunrise. Farmers were out milking their cows. You could read by the aurora, and it was seen down in the Caribbean, Hawaii, and Singapore. Basically, the aurora kind of started at the north and in the south and worked its way to the equator. And basically, the north and south aurora auroral ovals met. They met at the equator. So the entire Earth was engulfed in this auroral ring. And of course, if it occurred today, it would be about 2 billion's worth of damage. You can see in this diagram here, this is one of the old magnetographs at the time. The magnetic field that was being measured, you have a top panel and a bottom panel. And in the bottom panel, the magnetograph went literally off, or I mean the top panel went off scale down into the bottom panel and back up. That's how strong the magnetic perturbations were. The guys who created this didn't even make a scale large enough to measure it, which is pretty insane. So you'd think that that's the only Carrington event that we've had in the last 500 years, but that's not true. We've actually had one, maybe even 2 of them recently. Part of the reason why we've seen so many Carrington events recently may have to do with this low solar activity cycle, and part of it may have to do with the fact that We have more satellites or more spacecraft in space than we used to, and so we're viewing more of the sun than we used to. Whereas Earth used to be a lone little observer, now we've got multiple satellites or multiple spacecraft orbiting the sun, and so each of them can get hit individually. So now we're beginning to realize, you know, Carrington-class events are a lot more common than maybe we first realized. So here's an example of a Carrington event back in 2012. This is a model. This is Enlil. This is now NASA's version of the model. And what you're looking at in this panel here, whoops, I just died. Shoot. Yep, we're done. Damn. Why aren't you charging? Unbelievable. Yep, I'm done. My iPad just died. Wait a minute. It's showing me still on. How is that possible? Okay. Am I still live without my iPad? Are you kidding me? I'm staring at my presentation right now. I'm not running... Wow, that's really cool. I'm running a Sling Studio, and I have a controller, that's my iPad. And the bottom, I'm using camera links and stuff, so they're still all running. But I thought if I lost my control interface, that would mean that everything would still be, gone. This is cool. Okay. Oh my gosh. Well, yeah, but, okay, for some reason my charger, I'll pick it up and show you. See, this is why I need to edit these mini courses. Live is always fun, isn't it? So here's my dead iPad, and here's the charger it's been plugged into. And it was working just fine. But it wasn't, I mean, the charger had been working just fine. And then suddenly it stopped. So I'm not sure what happened, but I will now try to continue this broadcast, you know, I guess free range now. I don't have a controller. So we'll see how long this works. And I'll just periodically check. Yeah, it's the CME that hit. That's right. I got hit by a solar storm, I guess. I don't know. But yeah, okay, as long as we're still live, I'll continue. All right, let me try to get back to this here. So, and then I will just check in more periodically because I have no idea what I'm doing now. So, because I can't see myself. So the Carrington event of 2012, as I was on, hopefully I'm standing in the right place. I'm not sure I am now. This is kind of scary. Let's see. You should be seeing me. Gosh, I'll have to, hold on, let me just check to make sure. Sorry, guys. Because what will happen is I will stand right in the way of where I'm supposed to be looking. So I've got to orient myself left and right now. Okay, so if I stand on this side, right. If I stand on this side, I'm in the way. Okay. Thanks for that. Hold on. Now I'll go back to presenting, and I will stand on the other side. Let's hope I can remember that. Okay, so now we're looking at the Carrington event, and this is Enlil. This is NOAA's version of the model. So you're looking at the sun from the North Pole, and I don't have it annotated, but I bet you can spot that Carrington event coming out, right? Ready, 1, 2, 3, blammo! There it is, right there, going off to the north part of that, or I mean that direction over there. That is the 2012 event in July that passed over. See that red dot? Right, that red dot up there, that is the Stereo A spacecraft. I think it was Stereo A. Is it A or B? Yeah. It was a Stereo A spacecraft, and as you can see, Stereo A went right through the middle of it. So it caught everything, the core, it caught the envelope, it caught the strongest part of that event, which is not always easy. But what we learned from that event when it hit us, and you can see how incredibly big it is, what we learned from that event, and now let's see, and let me stand on this side so you can actually see the magnetic, you can actually see the plot now of the field components. And hopefully you can see, you got density at the top, you've got the shock, which means that's the velocity right there, the second panel. The third panel is temperature, so don't worry about it. The magnetic field components are kind of in the middle, and they're done by, they're done in a slightly different way. We call them the RNT system. And that is slightly different, not completely, but we're not going to do our little right-hand rule thing because one of the components is reversed. And then we'll get all our handedness wrong and it won't work. So don't try to use your rule on this because we're in a different coordinate system. It's not the XYZ. The RNT has a reverse transverse component. It points what is east was west and what was west is east. So don't worry about that. But if you can look at it, you can actually see that is the stereo A data. There were actually two ICMEs. You had the first one in gray, a small gray one, and then a second in a much larger gray. And this was an incredibly complex event. There was actually even events before this that kind of what we call preconditioned the solar wind, which means that if this had been Earth directed, oh my gosh, it would have been like the perfect storm. Because when you precondition and blow all the junk out of the way with a smaller ICME before the big one goes, it just means the big one is unimpeded, and it just can blast and give the biggest, the most intense impact that it could possibly have delivered, because nothing is slowing it down. So the speed of this event was well over 2,000 kilometers a second. Typically, ICME speeds, even with really intense events, don't get over about 1,000 kilometers a second. The magnetic field strength was peaked over 100 nanotesla. Just to give you an average, a nice decent storm, a G2 or G3 level storm, can have magnetic fields only of about 20 nanotesla, so think about 5 times more. The southward field, just in of itself, was over 60 nanotesla. I don't even remember, since I've been studying these structures, ever seeing an earthward directed event that had a southward field of 60 nanotesla. Just never seen it. And some of the solar, just to give you an idea, some of the solar wind measurements actually had to be reconstructed. You can see some of the different colors in these panels. Some of them had to be constructed from, like the proton temperature had to be reconstructed from the electron temperature. We had to use oxygen isotopes, oxygen 6 and 7, to kind of help reconstruct the velocity profiles. The instruments were overwhelmed by not just this event, but also I think the solar radiation storm that was associated with it. So this was a very, very intense event. And like I said, it was just a couple years ago. Now here's something interesting, and I don't know if I can get completely out of the way for you, but I'll try. Let's see, I am on this side. Okay, so this event, this is the Carrington event you just saw, right? And you can see it lifting off to the off this direction. Now next to it, on this other side here, and I can now move over here. This second event was the event that happened in 2017 when we had Irma and remember Irma and Harvey? Remember when Irma was decimating Puerto Rico? One of the events in that September of last year was this huge monster right there. Now you can tell, if you compare it to the Carrington event of 2012, you can tell this event that happened in 2017 was slower, right? So was it a Carrington event? Not quite. Was it a Carrington class event in terms of size and intensity? Probably. And if you notice, this event actually clipped us. We actually did get a geomagnetic storm at Earth because of this, but so did Mars. If you look, we actually had a radiation storm from this structure that actually hit Mars and enveloped that planet and hit it far worse than what we got. But it's very rare to have an event be so incredibly big that it gets all of these different planets at once. So this was a very, very surprising event. And so what that makes is essentially in this solar cycle, we've actually seen at least 2 Carrington or near Carrington class events, just in this cycle alone. Okay? So the idea of a once in every 500-year storm, maybe we got that wrong. Maybe that was just a product of bigger solar cycles, which have a tendency to not launch as many Carrington-class events, and the fact that we only had one event that we, one spacecraft, and that was Earth, essentially, or a spacecraft at Earth. We didn't have I don't want to say armada, because we sure don't have that yet, but we have a lot more spacecraft out in the heliosphere taking measurements of the solar wind than we've ever had before. So we have a much higher chance of seeing these structures, and now beginning to really realize how often does the sun fire these things. So now looking at this event, what I wanted to do was put this and see if I can, let's see, if that's on that side, okay, then I'm probably standing in a good place. That structure, as you can see, blowing off up at Earth, this is where I'm going to talk just a tiny bit about the radiation storm. Now, if you recall this structure here, this diagram, this is what I opened with, right? So here's our solar slinky, and that dark line is the shock in front of it, right? That shock is what helps drive radiation storms. And so if I flip that thing over, so now it's pointing upward. The reason why I did that is so it can align with that big near Carrington class event that blew out in September of 2017. You can see now how they're kind of aligned, right? You can see how they kind of look the same. Imagine the huge shock wave out in front of that big red bubble as it moves out. Now imagine if you're anywhere near that shock wave, you're going to see the radiation storm that is associated with it. Sometimes the radiation storms end up being even more intense than, maybe the most impactful thing of a Carrington-class storm, because they're just so incredibly strong. Let's take the ground level event on Mars from this event, and I'll just read it. Radiation levels suddenly doubled, and they remained high for nearly 2 days. Okay? This is Curiosity, right? They had to shut, I think part of Curiosity they shut down, or this is what the reason why they ended up shutting Curiosity down anytime there was a threat of radiation storm. It says this is the biggest event we have seen since Curiosity landed in 2012. So there was the ground level event. You can actually see it right here, and I'll stand on this side right now so you can actually read this part. You can see how much radiation, the big dose rate that they got, how big a bump they got there. And this is insane, because when you think of us wanting to colonize Mars, Mars doesn't have anything like a big magnetic shield around it. Its magnetic shield is much, much weaker, and it's not really coherent, because Mars isn't generating its own dynamo anymore. So the whole atmosphere, and even clear to the ground, is far more susceptible to radiation storms and big solar storms like this than we are even at Earth. But even with Mars having this huge impact, we still got part of this. And Mars is on the other side of the sun. So what does that tell you about the size of this event? Right? I mean, you can see it in the model there, right? We're looking down again from the sun's north pole into the ecliptic plane where all the planets are. And you can see some of the planets labeled right there by the colors. But, oh my gosh, I mean, what a huge impact to have a single event that can reach both Mars and Earth at the same time. How incredibly big does this structure get, right? So when you think about scientists and these cute little solar slinkies, think about the Carrington event and think about how massive these structures can get. And it gives you an idea of what we're dealing with, and the massive challenges that scientists have trying to predict their structure as they're being blown out in the solar wind, let alone anything else about them, their impacts at planets. So as a reminder, here's the perfect storm. When we had region 2673, it was because of the region on the sun, and well, I'll stand on this side for just a second. So you can see region 2673 in that gray magnetogram picture. I'm not going to go over in detail what that is, but it was just know with all the color mixing on that sun, it changed very, very rapidly, and the growth was very scary, and we knew it was going to be an ugly player. And sure enough, it got so ugly, it was just firing off solar storm after radiation storm after solar flare, boom, 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 boom. And you can see that one solar flare that it fired, that I've got an arrow at, that blue sun right there, that That was the one, that was the event that launched both, or that fired both that flare and launched that big near Carrington class CME. So you can tell where that event happened was literally on the limb of the sun, the edge of the sun. And with it being on the edge of the sun, that means that that event wasn't fired at us at all. As a matter of fact, it was slightly occulted. It was actually fired a little bit behind the limb. And that big coronal mass ejection that was launched was so large that it still hit Earth. And I always tease people saying, it's kind of like if you had a gun and you fired the gun away from you, right? But the gun fires such a big bullet that it still hits you. I mean, it's just insanity to think about that. But that's what we had with this event. And of course, Irma, I think I'm standing where Irma is, was right over Puerto Rico, decimating Puerto Rico. We had solar flare after radiation storm after solar flare after radiation storm. Anybody who's a ham radio operator hated this period because they could not do anything for hours upon hours upon hours. And that is what it's going to be like in a real Carrington event. I always love how people focus on, we just have to worry about the geomagnetic storm. No, you don't. If something launches a Carrington event, a Carrington class event at you, it's going to launch all this other junk too. And it's going to probably continue to fire more junk at you. And it may launch 2 Carrington class events, not just 1. It may launch a whole series of stuff. And so you're going to be dealing with ham radio out, satellite radio out, radio bursts going all the time, satellites themselves failing. You're going to be dealing with a whole slew of stuff. And it's always silly when people talk about, you know, needing to get to a Carrington class event before things become dicey. And it's like, no, you can have a near Carrington or even something less than that and have it wreak incredible havoc all over the planet because it's not going to act alone. It's never going to be alone. And that's not a dialogue that I think anyone ever has. And they really need to. Because when we talk about communications during these events, and they say, well, we need to have someone in the loop who we can call down if there's a national grid emergency. We need to be able to talk the manual operator through it. And I'm thinking, what phone are you going to use? If there are M-class flares and X-class flares going on all the time, your power is out. What are you going to use, satellite phones? Right, radio bursts, that takes that out. You know, are you going to do search and reconnaissance, or search and rescue, or reconnaissance, looking at your power grid lines, seeing what's damaged, what needs to be redone, what the infrastructure problems are? GPS most likely won't work. How do you plan to mitigate all of this stuff with more infrastructure being affected than you have even bothered to consider? And it's all going to be affected at the same time. This is why the smaller storms are so important. They give us test beds. They give us an understanding of the magnitude of these storms and what things are going to be impacted when and how much altogether as a system. These are the things that nobody talks about. We have to look at this weather as a system. And that's really where I'm trying to push this. So speaking of as a system, here's some of the effects. These are all done by field reporters just like you guys. I got every single bit of this information from all of this. Here's what Aurora looked like in New York. Aurora was seen clear down to Arkansas. Here's what Brazilian television looked like, right? DirecTV. You guys can read, you know, Spanish or Portuguese or whatever language that is, one of the Romantic languages. Basically saying that there's solar interference. That's because we were having radio bursts all the time that was taking out DirecTV. Here's what the CW, the reverse beacon network, looked like. This is CW signals. These are Morse code signals, which are the most robust of all ham radio communication. Look at North America. During that flare, they're gone. You got it all over the UK, sure, and Europe because it's nighttime. They're being shielded. They can't see the sun, so the sun's radio bursts can't affect them. But look where everybody else is going, right? And then this, believe it or not, was sent to me by a field reporter showing me that the Russian state network REN TV actually picked up my forecasts. They took them right off of YouTube and they broadcasted them. And I'm so forever grateful because they were talking about Hurricane Harvey and Hurricane Irma and all the hurricanes at that time. Maria, I think, was right after it. And they were talking specifically about emergency response and how difficult it was going to be at the time. And this is what I want to do with American television, Canadian television, European television, UK television. We got to get the meteorologists to start broadcasting this stuff because it is a system. And when systems get impacted with these big events, people need to know because it matters. It's life altering. So, Carrington in the space age. Outside of the 2012 event, that was a Carrington event that didn't hit Earth. We actually have had a Carrington class event that did hit Earth in the 1970s. Now, I talked a little bit about this. As a matter of fact, this is a slide from my last class, so I won't go over it in real detail. But this was, once again, a white light flare, just like the one Carrington saw. We had gamma rays, we had white light flares, and again, this was a series of events that occurred. These Carrington class events do not happen in isolation. They happen as a series. So where there's madness, there's going to be more madness. And that's something that we really have to deal with when we think about these events. Okay, the Carrington class CME hit Earth on August 4th of 1972 after a very large flare. Took something like 14 hours to reach us. We also had a huge radiation storm that was associated with this event, and I'll talk a little bit about that. It destabilized portions of the North American power grid. It tore a hole in the ozone layer, the radiation storm did. It rattled Earth shields so much that it triggered the detonation of sea mines in Southeast Asia. Okay? And it was a huge long-duration radio disruption above 1 gigahertz, which means GPS is gone and so are satellite phones, and a lot more. Now, thank you to Dolores Knipp. If you guys have not read her paper on this in space weather, you really should. It's an open paper. There was a lot of declassified documentation that she then reviewed and wrote up in terms of its space weather issues. One of the big things that people don't realize is that radiation storms, they don't just cause havoc for navigation and satellite systems. They actually change our atmosphere completely. And this particular event in 1972 was one of the biggest that has done so, but it is not the only one. In fact, the 1989 event also changed our atmosphere, along with a few other storms. The ozone layer is not as robust as we'd like it to be. And so radiation storms, when they're big enough, can actually tear holes in it. And it takes days, if weeks, months, sometimes years, in order to get it back to where its pristine state is. And in this case, the radiation storm in 1972 from this Carrington class event was so big that it caused a hole that was open, that stayed open and didn't even change. I mean, it just stayed that open for over 50 days, which is the longest we've ever seen it. Now, I've seen other studies done. This ozone hole, and oftentimes ozone holes caused by these things can take years, up to 4 years for them to close. And in this case, it was no different. It took about 4 years for the ozone to completely repair itself. These are simulations, mind you. These weren't measurements, but they're simulations that have indicated that that would be the case. And yeah, I think I did write that down. And then on top of that, these radiation storms can change our atmosphere so much that it can create a new layer, a new atmospheric layer in the ionosphere. In this case, there were Russian amateur radio operators who were reporting a temporary, like a sporadic E layer that was being formed at night during the solar storm, during the radiation storm. So, you know, there are a lot of solar geophysical coupling. There's a lot of things that can happen with these solar storms that cause a lot of parts of our upper atmosphere to change, and we don't really understand them all that well. It's one of the reasons why I know a lot of people harp on HAARP, but it's one of the reasons why HAARP is still a very important scientific tool. We're trying to understand this stuff. We're trying to understand how does the ionosphere change when the sun does something to it. And unless we're able to probe it and cause these things to happen ourselves on a very small scale, then we'll never get further in understanding how it all happens. But we need to, because this kind of thing is real, and it does happen more often than we'd like to think. We were able to do some solar wind forensics from a couple satellites. This was definitely the fastest CME ever recorded. You can see here I've got velocity, temperature, and density on here. The velocity, let's just look at the velocity for a second. It was over 2,000 kilometers a second by the time it reached Earth, this particular Carrington class CME. 14.6 hours from the sun when it was launched to Earth. It's hardly half a day. They considered that the average speed, because we didn't really have coronagraphs that were working. If you guys look back, I think OSO was flown in 1971, so we'd barely gotten it up, or we were just getting data from it when this event happened. We had no idea what we'd even be looking at, because we didn't even know how to observe a coronal mass ejection being launched from the sun. Take a look at my prior class if you want to know the history of when we really started understanding what we were looking at when we were looking at the sun's corona. And it was really right about this time. But when we look at the average transit speed, if it arrived in 14.6 hours and we know the distance from the sun to the Earth, it's pretty easy to figure out what the average speed must have been. Almost 3,000 kilometers a second. That's insane. We've never seen anything that fast before. And by the time it reached Earth, it had only slowed down to about 2,000 kilometers a second. Unbelievable. There was a huge density enhancement in front of it. Obviously, if it's plowing through the solar wind that fast, there's a lot of stuff that's going to pile up in front. Remember I talked about that draping field? Absolutely. We could have started to get a solar storm just from the draping field at that point. But we didn't have a lot of instruments in the solar wind at the time to be able to talk about it. Dolores was talking about there might have actually been possible shock structures inside the sheath itself. So inside that draping field, there might have been shocks going on inside it. It was so dramatic and so much energy being plowed into that, and so much acceleration of the stuff in front of it that we could have actually had multiple shock waves just in the sheath itself before we actually hit to the big obstacle. And we got lucky, believe it or not, from this event, because DST, which is one of the ways we measure the strength of a solar storm, only got to be minus 125 nanotesla. So what does that tell you? Does that tell you the field strength, the field in this thing, even though it was incredibly strong, the field was most likely northward. So the solar slinky that hit us wasn't pointing the right way. Thank goodness, because it did enough damage even as it was. What happened in this case was just the impact, bam, of this thing hitting our shield. Even if this thing bounced off the shield and moved off because it couldn't couple, it wasn't turned the right way. The magnetic field wasn't southward. So it squished our shield, but it didn't couple with it. It didn't unite with it and become one structure. It hit our shield and kind of distorted and bound, and we went through it, right? We went around it, kind of kept our own little identity, our own little bubble. But it smushed the Earth's shield so much and smashed it so hard that we got an EMP from it, right? When you move a magnetic field very, very quickly and squish it, you make it stronger. You squish and compress that field, it gets really strong. If you do it really, really fast, boom, you induce electric currents really, really quick. That is an EMP, okay? It's an electromagnetic pulse, and it happened from our Earth. Just from that electromagnetic pulse, we got huge voltage swings in the northern tier of the United States. And this pulse, all of it happened under 5 minutes, okay? So you want to weaponize a Carrington event? Yeah, that's how you do it. Get the Earth shield to compress so much that it causes an EMP. Under 5 minutes, you can get a horrible amount of damage. And this is what happened. There was an outage on the L4. This is an AT&T cable network. They induced electric fields of 7 volts per kilometer, which exceeded the high current shutdown threshold. This was also coincident with fluctuations in the Earth shield of about 800 nanotesla per minute. This is outrageous. We've never seen anything that high. And this was literally within 2 minutes. So we had we had magnetic field changes of 800 nanotesla a minute for multiple minutes. And this was just, no grid could handle this. In northern Canada, it was even worse. You had over 2,000 nanotesla a minute. And this caused the Manitoba Hydro Company to see 120 megavolt drops in their power supply to their customers. All of this happened in 5 minutes. You can't even react in 5 minutes to see 120 megavolt or megawatt drops in power supply. Other longer lasting effects from the actual storm itself. In Newfoundland, the GICs, these are the currents that are induced in the ground from the actual during the actual solar storm. Now the Earth's shield is wiggling. It activated the protective relays numerous times between August 4th and 5th, and they also saw strong GIC effects in Ohio and Maryland. But again, this solar storm itself wasn't strong. What was strong was the impact, because the magnetic field of this thing was pointing the wrong direction, most likely. We don't know. But if you look here on this plot here, I'll stand on this side. Wait, am I standing? Yeah, I'm standing on the right side, I think. Now you can see in this plot, maybe I'm not. I'll stand somewhere, I'll stand off completely to the side because I can't remember. You'll see if you look on this plot, the power system disturbances. You can see strong, moderate, weak, right? And you can see all of these different networks that were reporting power issues, the grid issues, back in 1972. And remember, this was all within 5 minutes of the storm, and this is due to a northward pointing Carrington event, not a southward pointing. So now the super solar storm swept this Haiphong, I'm probably mispronouncing it, my apologies, minefield. This is a minefield near Vietnam. There's a document from Hartman and Truver that was declassified, in which he had said, the authors had said, the Haiphong destructor minefield was actually swept by a solar magnetic storm in the August of 1972. And you can actually go online. I've got a link right here. Gonzalez, I can't remember if I'm standing in the right place or not, but Gonzalez et al. Talked, and here's another quote, and this is again straight, Dolores Knipps has managed to find these and pull these out. I added a little bit more text here at the end, but it said, during the first few weeks of August, a series of extremely strong solar flares, they really mean coronal mass ejections, caused a fluctuation in the magnetic fields in and around Southeast Asia. The resulting chain of events caused the premature detonation of over 4,000 magnetically sensitive destructors, DSTs, which were over half of the DSTs planted over the past several years. And poor Gonzalez was lamenting the fact that they had to go back in and reseed the minefields, and it was an outrageous amount of work that they had to do in a very short order. Because of the politics and the tension of the time. I mean, yet they weren't able to talk about it. They weren't able to do anything because it was all classified. And nobody wanted anyone to know that a solar storm, the EMP of a solar storm just went pop, 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 and blew up 4,000 mines. Here's an example of the mine, that picture. I don't know if I'm in the right place or not. But the picture shows a boat going by one of the mines and detonating it. It's the magnetics in the hull of the ship, the magnetic, the metal. It changes the magnetic field locally, and if your DST is sensitive enough, it recognizes that change in the magnetic field and it'll detonate. And that's what the solar storm did with that EMP. When it compressed and released, it detonated everything that had a threshold set low enough to be able to cause that to happen. And nobody talked about it forever. So that's how incredibly powerful Carrington-class events can be, even when they're pointed the wrong direction. Even when the solar slinky is not the strongest part of the structure. The strongest part in this case was just the impact against the Earth. That is what really did the damage. So anytime people say, well, solar storms you have to worry about just the GIC impacts. You just have to worry about the storm itself and riding through all of the havoc that over several days from the storm kind of causing these currents to build up, and the aurora and the radiation storms and stuff like that. You also can get it very, very quickly from almost what we call the sudden storm commencement. And that's just when the thing actually hits Earth and compresses Earth's magnetic shield. It can create an EMP, and that's oftentimes talked about as the E3 component of the EMP, when there are different types of fast-acting EMP, a slow-acting EMP. This is on the slow side. They call it the E3 component, but it does happen with Carrington-class events and even lower-class events. And it's much more, the low-altitude areas of Earth are far more susceptible than the high-altitude areas are with a sudden storm commencement if they're small. But with a Carrington-class event, all bets are off. It's the whole Earth that gets walloped. Okay, so now let's quickly talk about the future of space weather. If we talk about forecasting for the red planet, you know, everything that we've learned about Earth is that has taught us how much our Earth shield protects us. Mars is not so lucky. As I've mentioned before, there really isn't an intrinsic magnetic field that can protect Mars. Now, granted, because of that, they don't have to worry about the EMPs that you get from Carrington class events necessarily, but they have so much more to worry about. For example, if we take a look at technology-savvy millennials that call themselves the Mars generation, then we can easily translate that into saying, well, Curiosity must be the first of them. And after that Carrington class event hit in 2012, they made it routine for Curiosity to shut down. They basically said, you know, they'd even tweeted out when Curiosity was tweeting very frequently, and you could see a tweet there that says, "Storms are coming. There's a solar storm heading for Mars. I'm going to go back to sleep to weather it out." And you can see how many times it was retweeted. And this idea that radiation is a radiation storm, even from just regular big solar storms heading toward Mars, that could be a problem not just rovers, but for for people, colonists. It's very serious. It's very real. Mars doesn't have protection. As a matter of fact, it doesn't even have communication when there's a solar storm. You get a solar storm hitting Mars and the entire atmosphere goes opaque. You can't get a signal in or out. You can't do over the horizon communications. You basically are radio dark until that storm passes, simply because the atmosphere is so lit up. You can't do anything. And it's a very different world than it is here on Earth when it comes to trying to colonize it and deal with all sorts of impacts, space weather impacts. Space weather is almost as important, if not as important, as dust storms and the terrestrial weather on Mars. Here on Earth, we can kind of look at space weather and say, well, as long as I keep my boots on the ground and I don't care about technology, I'm fine. I don't need space weather. On Mars, you do, no matter what, because it'll get you, even on the ground. And this puts a whole new spin on the concept of the Martian and, little Matt Damon hiding behind his potatoes. It's not going to work. As a matter of fact, astronauts know that if they go to Mars, they're going to have to go into some of the natural fissures and craters. Some of there's these deep fissures in Mars, and they think that maybe they'll have to have bunkers in there and have to go underground in order to stay safe from things like radiation storms when they happen. And the idea of keeping the colonists safe, keeping doing over the horizon communications, all of this kind of stuff, these are questions that aren't being asked yet. And there's a lot of activity about sending people to Mars, and everybody's worried about just the interplanetary travel. And yes, we have to worry about that too, there's no doubt. But there's a lot of problems that have not been solved when it comes to communication and keeping humans safe once you're even on the planet. So, this is where space weather is going to be going. And we have to learn as much as we can about things like the Carrington event in order to get there, in order to even begin to leave our own planet on the way to colonizing others, especially ones that are even more susceptible to these big space weather events than we are. And so with that, I will pause and give it back to get back to YouTube and see if you guys have any questions. So let's see. God, I can't believe I'm still live. Hopefully I did okay, guys. I also have a space weather report. I actually did a Martian space weather report, but I've been on so long I didn't bother putting that up. So let's see. You okay? Hi, Susie. Let's see. A flame. Okay, that's great. Yeah. I am impressed with those EMP impacts. Yes, I agree. No idea that they caused EMP. Right. Well, that's one of the truths about the Carrington events, is that they hit us from all sorts of different sides. And the idea that they don't work in isolation, that if you're going to have one of them, there's a good chance you're going to have multiple ones. Or you may have one single Carrington class event, but you have 3 other solar storms that are just a little bit less in intensity. Those things are very real. And then you're also going to have X-class flares going off and all sorts of other havoc. And suddenly, you know, a space weather event that you might have been able to survive on its own suddenly becomes much more painful and much harder. Okay, can astronauts be protected while traveling to and from Mars? You know, not very easily. I mean, there's a lot of people working on this problem. Water, I think, is the way that everybody's trying to go, to use water as a shield. But my gosh, if anyone's seen how many micrometeoroids and things like that are out in space and what they do, I think trying to just clear near-Earth space may be so hazardous that all the water is going to leak out from a million little pinholes. I mean, we'd have to shield the outside of these spacecraft very, very well in order to make sure that the water inside stays pristine so that it can absorb all the cosmic ray particles. And it's just, we don't have what we call a high TRL level, a technology readiness level, for us to be thinking, okay, this is going to work right off the bat. And it becomes a little bit cavalier for some of these Martian, you know, flyby missions and proposers to say, yeah, the radiation problem is solved, no problem, we can get there. It's a bigger problem than we think it is, and it's more pernicious than we think it is. And there's a lot of partial solutions, but no solid silver bullets that are going to make it work. And again, that's only part of the problem. The interplanetary travel is part of the problem. Staying there on the surface is also another problem. And here's a funny little thing too. The interplanetary part is actually worsened right now. I know we have Mars coming closer to Earth than it ever has, and we need to get a mission out by, you know, before 2032 or something like this. Otherwise, Mars is going to be so far away from Earth it becomes a much longer mission just to get there. And I get it. But part of the problem is we're in the worst time for solar cycles right now. It's predicted that our solar cycles are going to continue to be low, which means we have a bigger chance for Carrington class events, and the cosmic ray penetration is 30% higher, or maybe even higher than that, than we've ever seen it in the space age, because our sun is so quiet. And so we don't have a big solar shield anymore like we normally do. And so it's absolutely the worst time to go to Mars. But, you know, we take advantage of windows when we get them. And if people are completely aware of the risk, then more power to them. I know Neil deGrasse said he would sign up in a heartbeat, and I think he's nuts. But if that's what he wants to do, okay. I just know a little bit too much about the weather to be one of the people who would sign up at this time. So hopefully that answers that. The sun's magnetic poles shift all the time. They don't make ours shift. That's very true. Our dynamo, our Earth's core, makes our poles shift. The sun's shift a lot faster than ours. So anybody who's worried about our shield shifting and causing problems, don't worry about it. It's happened before. It'll happen again. It'll make space weather quite interesting for a while. Space weather is beginning to get interesting now because of it, but it's not going to end life on Earth. So don't worry. Let's see. Is a slinky something like a tornado within a lightning storm? Not yes and no. I mean, no, because I'll say yes because it is swirly. No, because it's not stochastic. Magnetic fields are ordered, and they have forces that are governing their orientation and governing their curvature and stuff like that. Magnetic fields also can't. There's all sorts of laws that go along with it. When you bend magnetic fields, you cause electric fields. You create electric fields that then oppose that motion. Magnetic fields don't like to be bent. They don't mind being stretched. They don't like being bent. So certain field configurations, it's always going to try to relax to. And there is a kind of it's called a Lundquist solution that we think a lot of these solar storms try to relax to magnetically. They'll never get there because there's so many other forces on them. But there are some laws of physics that kind of keep these structures the way they are, and they fight to try to maintain that shape. Same kind of thing on the sun. The sun has a potential field, and it's always distorted from this potential field. But if it could ever get to what we call the potential field configuration, there'd be no electric currents on it. It'd be relaxed, it'd be quiet, and it wouldn't move. And it's always fighting to get back to that shape. And that's part of why we have all these transient events that are spit off. It's kind of, the sun is just trying to relax, believe it or not. Relax, relax. So that's what the sun's trying to do when it lets off steam, so to speak. So it's not really like a windstorm in that sense. Okay, so let's see, what other questions do we have? Would the new generation of vehicles that use computer controls be affected by the 1989 storm? No, but the control systems might. The nice thing about and this is what I always get upset at, like the History Channel or National Geographic or some of these shows that they put on that talk about solar storms in such a way that it makes it seem like it's going to affect your car electronics. It's going to affect your pacemaker, the currents induced in the ground. No, it won't. It's not going to bother that stuff because, pardon me as I adjust my mic. No, it won't, because these things are small, right? The reason why solar storms affect power grids is because there's hundreds of miles of stuff. I mean, if you had a pacemaker or a car computer the size of Lake Michigan, okay, maybe you have a problem, right? But you don't. You know, these structures are small, and so the currents that are induced really aren't that big. You have a tiny bit of current and a tiny bit of current and a tiny bit of current, and that's it. So it still adds up to a tiny bit of current or a tiny voltage potential. If it was the size of Lake Michigan, though, then the tiny current, tiny, add, over that huge distance, suddenly, okay, yeah, it matters. So really, it's the size of structures that matter when it comes to being directly affected. Of course, if you plug something into an outlet and, you get a brownout because your power grid is fluctuating, well, then, yeah, but you're not getting it from the solar storm directly. You're getting it because the power company is getting it directly from the solar storm. And that goes into things like, well, what can the public do to help mitigate? And I'm working on that. I've had some people ask me some questions recently about that. And I think there's a lot that the public can do. If we were to get a huge storm like the 1989 storm or even worse, what could the public do? Could the public turn off their power, reduce their power consumption? Because could we install rolling blackouts? Sure. I don't see any reason why we couldn't. We understand it when it comes to terrestrial weather, right? You got a hot day, okay? Too many people are using the air conditioners. Everybody try to conserve your power as much as possible. We get it, right? But people don't understand what a solar storm is, so they don't know, oh, why do I need to conserve my power today? But I think by raising awareness of what space weather is and what these big events are, we can do that. And then when we get a big enough set of people that understand what to do or understand that the public really has some power in this, then we can turn around and then talk intelligently with the power companies. And we can talk with your local weather person and say, okay, let's figure out a strategy of what to do when there is a solar storm. And eventually we could even try National Solar Storm Event Days, where it's like a fire drill for a solar storm. Okay, everybody, between 10 p.m. and 12 p.m., reduce your power, turn off all the appliances you don't need, blah, 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 blah. And we can see what kind of reduction on the load on big power grids, especially the susceptible ones, if it might have an effect. I think these types of exercises and ideas are not far-fetched. I think that there's definitely some dialogue that needs to be had here, but nobody's having it yet. So these are the things that I'm going to try to change, and hopefully with your help. These are things we can all change. Why doesn't modern forecasting incorporate space weather in their forecasting? That's exactly what I'm trying to do. The field hasn't been created yet. This is exactly what I am trying to do with this kind of thing, because it needs to be. Obviously, you guys see the need, and it is coming. Just, I need help. Raising awareness, talking to your friends, getting people to understand, talking to your local weather forecaster and say, hey, I need space weather. Get the space weather. I know it's out there on YouTube. Why isn't it on mainstream news? I am actually trying to help train weather broadcasters in this art, and we will get there. I'm working with Millersville University. We've got a curriculum that we are hopefully going to roll out in the fall of this year for not only students of meteorology, but also practitioners in the field who want to learn space weather. And we are creating a certification for this that hopefully eventually the AMS may adopt for broadcasters. And so in other words, it's going to give a lot of these people the same kind of information I'm giving you. It's not physics necessarily. It's not hard, you know, you don't want to become a scientist, but you want to be able to know enough to be able to do the right things if a solar storm like this were to happen. So hopefully hopefully that gives you an idea of what I'm trying to do. Helicity is a component in tornadoes. Oh yeah. True, but that, again, helicity is a component in anything that swirls, right? It's a component in DNA, for goodness sake. So it's just a way we classify things as scientists. Although helicity is not just handedness. I have to be careful. I'm going to get slapped on the back of the hand. Helicity means something very, very specific to scientists. So it's more than just handedness. I was talking more about handedness. Helicity has an actual physical meaning in space physics, which I won't go into right now, space and solar physics. Would that 1972 E3 EMP, if it happened today, damage all of our electronics? Oh yeah. We would be in real. You know, there's a lot of questions about that too, because it may do a lot of damage to the grids, maybe even more than before. But it's the funny thing is a lot of the national grids now are getting savvy. They realized that back then we actually had a lot of robust stuff because it wasn't. We had things that were far more mechanically based. Now we have things that are, you know, solid state or much more electronic, you know, in their nature, and so they are a lot more susceptible, running on lower voltages and things like that. Back then, the big old relays, you know, those things could survive. I mean, you may flip them, granted, but just flip them back and start them up again. They're fine. Now you fry them and they're dead. So a lot of the grids now and these consortiums are building, they either are building or they have old, antiquated devices in storage, waiting for exactly this type of thing. So have faith in a lot of your local utility companies. They are working this. They know these things are problematic, and they are finding their own ways, slowly but surely, of having backup systems. And some of these backup systems are literally ones that, you know, require us to go 30 years or 40 years back in time to the old mechanical stuff that could not get fried like an electronic device could today. So, you know, there's pluses and minuses to all of that stuff. But we just continue needing to build the awareness in the public, and building the awareness with operators and you know, people who are running the grids, to get them to understand some of the things that they aren't taking into consideration yet, because they may not know the solar phenomena well enough to understand, for instance, oh, wait, I need to protect my grid not just from one of these things, but how many? What do you mean my phones won't work? I've got a satellite phone. It should work. It's got a battery. It's got, you know, what do you mean I can't call my operator down in Tallahassee? You know, you're like, well, they got the radio burst going, and that's going to knock out your satellite phones. Yeah, but I need to get a hold of them. Right. How do you do that? So, you know, there are issues that we need to help these people still understand that they don't yet. Have you set up your own solar alarm system? No, I don't. I guess we can't trust the governments to do the chaos, due to the chaos. You know, guys, there's no, I mean, everything's going to be chaotic if something as massive as that happens. My job is not to create I don't want to be a solar warning system in of myself. That's not what I'm trying to do. I'm not trying to build an empire like that. I'm trying to educate I don't want to reinvent the wheel. I want to educate the people that are already out there, the infrastructure that exists. And if we can educate them enough, man, the information will spread like wildfire. But we have to use the infrastructures that are already in place to make sure that it all spreads out as fast as possible and it gets the most eyes on it as possible. So that's to me, that's the charge that I've picked up, is let's educate everybody out there. All the meteorologists out there. Those meteorologists then get into everybody's living rooms at 6 p.m. at night every single day. Let them educate the senators who are sitting back eating dinner with their family and friends. Let them educate the lobbyists. Let them educate all the people that need to be educated. Let's make space weather part of our daily dialogue so we don't have to worry anymore about educating people. It's just weather, and people then get it, and it becomes a higher level of importance and priority in their lives, and it becomes an easier thing to talk about when it comes to, okay, how do we spend money mitigating this stuff? Why do I need to fly that very expensive satellite? Oh, space weather. Oh, here's the money. We understand. Please keep us safe. Get it? That's what I'm pushing for. But I'm not trying to make a counterculture. That's not really what I want to do. I know I'm skipping over some of these guys. I'm sorry. Let's see. You look like an 80s music video. Right, I know. Don't you love my groovy green screen? You know, tell me if you like it or if you want me to go back to the old TV. I think this works better, but maybe not. Yeah, I know it's a psychedelic thing with this YouTube thing in the back, isn't it? Let's see. They want chaos and expensive repairs. No. Look at Google. What? All the rivers carved gorges all the way down to the bottom of the oceans. Oh, come on, guys. Help me out here. Give me decent questions. You are doing a very good job of educating. I just wish more people were watching. Yeah, I you know what? I'm afraid that my thing did not put it up as public again. Every now and again, it puts it as unlisted, and I try to switch it to public, and it stays unlisted, and it just irritates me to death. And it happens, it happens. So let's see. Weather Channel people have been told not to tell 8 billion people that this is coming. No, that's not true. I have people from the Weather Channel I talk to on a daily basis. They're thrilled about learning space weather. They want to be able to do this kind of thing. All right, so I think solar weather is far more dangerous than the debatable climate change. I'm not a disbeliever. I just think it's overstated. Yeah, well, you know, the thing about space weather is that if it happens, it's going to happen fast. Climate change, if it's a death, it's a slow death. So yeah, I think I agree with you in that point of view. And there's I think Chris Mostel has a cartoon up on his, I think on his Twitter feed. Chris is a very, very renowned and scientist in space weather. And I think he has the cartoon that says, oh wait, he may have a different one, but the cartoon I love has like this timeline of scary events, and it says certain things about, like, you know, a volcanic eruption, you know, a climate change theorist, and you go this direction on the timeline, and it's more scary, you know, things that are not very scary and things that are incredibly scary. And at the very top of the list was solar physicists talking about, you know, a Carrington event or something, you know, or the sun just blew up or something like that. But it was the top of the list, and it was very funny. I think they called it a solar astronomer at the time. But I started laughing because, yeah, you know, if the sun decides to send us a monstrous event, it could be cataclysmic, right? And you don't have much time, and there really is no debating what is coming and what it could do to you. So yeah, I agree with you. I think space weather is what they call the high impact, low frequency event. Climate change is something that is, you know, on a much longer time scale. So we can all debate that type of stuff and how important it is, where it fits in the relevancy of our daily life. So I think I agree with you with your assessment. Okay. So I wish I could go study this properly. Yeah, you know, it's it takes time. You know, I spent more years than I care to talk about. It's not just getting the degree. Where you land in terms of the type of job you take is also very critical, because really, you could live your entire life in academia and not have a clue about the impacts of space weather. I mean, you hear about them here and there, but you really don't live it. You don't really understand it. So depending upon the type of job you get, it either isolates you from that aspect or it immerses you in it. And I just got lucky. I ended up taking a job that I wasn't expecting to take. And it immersed me in a world that I had no idea, that these events that I had studied so closely as a graduate student were wreaking havoc over here. And it really kind of brought two worlds together for me. And that's when I realized, okay, from sun to mud. And I had already had the sun part, and now I was getting the mud part. And then you guys really, you put the whole picture together for me, because when I reached out to you and saw how much it was impacting you, it was like a triangle kind of thing. The whole triad kind of came together, and it was like, wow, okay, this is what space weather really is, and this is why it's so incredibly important, and why there's such a huge part of it that's about weather, and not about space science. And I, you know, if I talk about it too much, I'll cry, because you guys really, you you really gave me a perspective that I otherwise would not have had. And that's why this has become such a labor of love for me. And with that, I guess I will, I'm not sure, do you guys have any more questions? I can check Patreon really fast to see if there's any more questions. Do I believe in the are you asking me, do you believe in the micronova theory? No, I don't, you know what, I don't even know what micronova theory is. There are a lot of things about fringe science that is wonderful because it forces scientists who are trained specifically to think out of the box, and it helps connect fields in many ways. So there are a lot of positives to what's considered fringe science, but then there's a lot of overstepping of bounds. And star water, for example, is one of them. How could a CME replenish the ocean waters in Earth, but not on Venus or Mars or anywhere else that CMEs hit? How come all the planets in our solar system aren't covered in water then, if it's done it for Earth? There are a lot of really kind of crazy theories that float around that gain traction, and it's kind of scary that they do. But I doubt I would believe in the micronova theory, but I will be the first person to say I'm not an astrophysicist, and I'm not a solar physicist. So my expertise may not be the right expertise to decide yes or no. The physics knowledge I have is very specialized, and so I have a tendency to outsource stuff that I don't understand, and I have no ego about saying that, because I think that's part of the being truthful and trustworthy. And so that's what I will always try to be for you guys. Okay, so this looks like it's about it. Let me check really quick to see if there's anybody on Patreon who has asked questions of me. I don't see anything yet. Hang on, guys, sorry. My computer is not reloading. No, okay, good. Everybody knows to go to, I've sent everybody to here, which is good. But it does look like, as I can tell by the number of people watching, it does look like this ended up being an unlisted video. Oh well, you guys got to be my smaller audience today, which is great because it probably meant that I got to answer a lot more of your questions. So you're probably, hopefully you guys enjoy that. So if you have any last second questions, let me know now. And then if not, then I will say goodbye. So let's see. Okay, the universal show. Looking at the sunspot activity over the years, are we predicting that we are going to have a major influx of them in cycle 25? It looks like cycle 25 might be a little bit bigger than cycle 24, but pretty much on the same order of magnitude. In April, that's when the Space Weather Workshop is happening at NOAA. There's going to be a whole contingency of solar physicists getting together. These are the ones that do all the modeling of the solar cycle, and it's a specific meeting in order to get the next predictions up in line. Will we have a consensus on when solar minimum is? No, guaranteed not. Solar minimum will be decided upon after we pass it. I guarantee you we will not have a consensus on when solar minimum was until maybe another year or two from now. There will be a lot of conjecture. There will be a lot of scientists saying, I think we've passed it. I don't think we're there yet. And a lot of personal opinion, but the field in itself will not have come to a consensus until afterwards. And they do that on purpose because they want to make sure that they have enough information to be able to come to a consensus. You know, scientists love to argue. So, and for good reason. I mean, that's the whole point of science. So we don't expect us to label when solar minimum is. Is solar cycle 25 coming? Yes. I think this rogue sunspot that we had today, the firing off the flares and the solar storms that are coming, is a very good indicator of it. We've already seen the currents underneath the surface of the sun. The jets are doing what they're supposed to do. We're seeing emergence of high latitude sunspots every now and again. So yes, solar cycle 25 is coming, but there isn't any indication that it's going to be much larger than 24. It'll probably be around the same. So hopefully that answers that question. If I get a chance, I'll look at the Diehold Foundation. Right now, I don't. I am so slammed, I can't even tell you. I have to go to ICI in April, the beginning of April, and I haven't even prepared for that yet. Hopefully Nariaki's not watching, so he doesn't know that. Will the recent eCME be Earth-directed? Yes, we may have 2 Earth-directed CMEs, so stay tuned. I will update on my Twitter feed. Looks like impact starting around the 11th, but could be as late as the 12th. And they'll be most likely weak. But yes, we could get aurora, maybe down to mid-latitudes. You know, it might be nice. And it could last for a day or 2. Okay, let's see. I recently moved to Oregon coast, and the sun seems harsher here. Is there somewhere I should look into this? I doubt it. I doubt it. That's probably more of an atmospheric phenomenon than a solar phenomenon. You know, you could talk to people in that area about what the atmosphere is like up there. If you're at higher altitudes, but you're in Oregon. There's no mountains there, right? You're not in a flat. You know, at sea level. That altitude may make a difference, but it's definitely not a solar issue. That's more a terrestrial issue, I would think. Okay, I've learned enough to be scared. I'm so sorry. Don't be scared. How about now, guys? Is the mic on? Okay, I've got sound. Good. How long till she figures it out? Now? Lost audio after answering comment about I've learned enough to be scared. Okay. Well, we'll see if my battery's dying. Boy, I've had a lot of technical issues today, huh? Okay. So what I was saying, I was answering the question about amateur radio propagation. And it was a question about will it affect it? And I said yes. During a solar storm, you will definitely get affected. If the storm isn't very strong, it won't be affected very much. Is it on? Yeah. My batteries are dying. How about now? Boy, I've had a lot of technical issues, haven't I? I don't know what to say today. And obviously, guys, you know, the class is over. I'm just kind of doing a fun Q&A for anyone who wants to stay. But don't feel like you need to stay. And it looks like the audio is still working. Okay. I need an IT person. Tell me about it. This is a one-woman show, man, and it's intense sometimes. But yeah, don't feel like you need to stay if you've already gotten all your good information. This is just a few extra questions I'm answering for fun, and I'll keep checking my mic down here to see if it's still on. But getting back to the HF radio, if the solar storm is not very strong, then it can help HF radio. It can also help GPS, especially at low latitudes. If the storm is strong, however, it won't help GPS, and it won't, and it makes HF radio interesting. During the gray line area, you could actually get north-south DXing, so north hemisphere to southern hemisphere and vice versa. That's something that gets really interesting during solar storms if they're big enough. And then also you get auroral propagation, especially on the night side. So what I was saying was that with a solar storm that's intense enough that you can get auroral propagation, if you're in the northern hemisphere, point your antennas north. Obviously in southern hemisphere, point them south. And because aurora rises and sets just like the sun and the moon do, then you could point your antenna northeast in the early evening after dark. And if you happen to stay on the bands a long period of time, then in the wee early morning hours, start pointing it, turning it more westerly, because you will be following the aurora across the sky. So yes, HF radio gets impacted quite dramatically. Okay, you do amazing stuff, not easy by any feat. Thank you. You can see the sweat dripping down my face, my gosh. No, women glow, right? We don't sweat, we glow. I forgot. I have to be more ladylike. Okay, how will Parker Solar Probe help with future solar wind predictions? That's, you know, the cool thing about Parker Solar Probe is that it's going to get us some, I believe it's going to give us some magnetic field prediction or views of the northern and southern poles, which was something I was talking about earlier. It's also beginning to change our perspective of the solar wind. In fact, if you were a Patreon member, you got my behind the scenes videos, I did a huge like 45-minute video on the insights from Parker Solar Probe because I've watched some of the talks and I've talked with Noor, who's the project scientist there. And he showed us some data that isn't published yet. And so I go into detail about that data. I don't show the data either, but I talk about what the implications are. And in that video, it really tells us that we're going to be seeing we're seeing insights into the solar wind that we never knew existed. The sun is so because of the way Parker Solar Probe is able to co-rotate. It's actually able to fly super fast and rotate with the sun. We're looking at the solar wind in a way we've never looked at it before. We've never been able to, and it really makes a huge difference in terms of our understanding. So it could absolutely create a paradigm shift in our understanding of the solar wind. So I glow well, thank you. It was a good show, too long to keep focused. Reminds me of my school days. Yeah, well, I had a lot of technical glitches too, so I might break it down into 2 shows where I just do the solar slinky stuff and then break and then show the solar storm impacts, because that was kind of a nice break right there. So still electron storm flux on GOES, but glad to see my magnetometer back working on GOES 15. Right. I think they were repositioning one of the GOES satellites at the time. So I saw that they were doing some repositioning work, and so there's all sorts of things that go offline when they do that. And someone else asked me that in a comment on YouTube, and I just said, you know, give it a few days, let them work it out, because I checked the OSO records and there was no indication of any anomalies. So I do think, at least I haven't checked recently, but I don't think there was an anomaly on the magnetometer. It's just that it went into a different mode, and they had to deal with, you know, all of that other stuff. Is propagation dead forever? No, it'll probably start increasing again. You may see it in the next 6 months if the solar cycle begins to get active again. There are indications, at least some scientists are saying that, and some models are saying that cycle 25 could start as early as this summer, believe it or not. Most people are saying probably not until the end of 2019, into 2020. But remember, the cool thing about solar cycle activity is that when it begins to ramp up, it ramps up fast. It gets so fast, it's so, a lot of activity super fast. So when the sun flips the switch, man, it's going to go quick, and we're going to see a radically different sun within a few months. Okay. Would love to hear you discuss MUF in relation to latitude for HF propagation during changes in solar cycle and CME timelines. Yeah. I'm working on an ionosphere class that will be geared toward ham radio, and I really, I've been working on it because ionosphere physics is not my bailiwick, and I'm only recently licensed as an amateur radio operator, and so and I have a technician's license. So my knowledge of the ionosphere and radio propagation is still ramping up. So unfortunately, I probably won't have a real class that would go into that level of detail for some time, because I don't even know. Gosh, I mean, it's so hard to even understand the ionosphere, especially as the solar cycle is changing. I'm beginning to understand it from anecdotal information that you guys give me during solar storms, but understanding it with solar flux changing and with the solar cycle changing, it's really tough. So I think that's an excellent thing, and it's definitely dealing with maximum usable frequencies for different solar conditions. I think that's something it's already on my list of things to do. But then trying to wrap in the solar cycle variability, that's a very interesting way of looking at it. And I might see if I can do that. But that class is something that's still in development. But thank you for that. I appreciate that, John. That's a really good idea. Okay. Let's see. I have a YouTube crush on you. Oh, dude with a laptop. Thank you so much. That's so sweet. I appreciate that. Hopefully you're learning something too. Let's see. I'm still trying to research to see if a low pressure system affects the propagation of radiation to the Earth. Yeah. Doug, are you the person that I talked to who calibrates radiation equipment? I was talking to someone who was calibrating radiation equipment, and I was chatting with a couple other scientists about that, and they thought that was a very interesting concept. The nice thing is that I'm getting involved with more meteorologists, especially working with the AMS, and so they're beginning to learn a little bit more about space weather and radiation, and I'm beginning to learn more about terrestrial weather. So as these fields begin to blend more and more, you will start seeing more of that kind of dialogue. But you are not the first. If you were not the person I was talking to before, you're not the first person to see stuff like that. That low pressure systems and high pressure systems seem to have some kind of effect when it comes to space weather, and it may have to do with the thermosphere-ionosphere coupling and the scale height, how things change as you go, as you get these high pressure and low pressure systems. So, what was strange about the growing sunspot AR 2720? You mean 2734, the one that's on the disk right now? That one is a mixed polarity between cycle 24 and cycle 25. It doesn't really belong to either cycle. It's what we call a rogue sunspot. Okay, guys. Is that a mason jar you sip from? Yeah. Yeah, it's a jelly jar, and I keep them as glasses just because they're easy. Let's see, do I ever look at the Earth as a brain the way the wind moves from it? I don't even know what that means. That's a really cool artist thing, though. I like the imagination that spurs. Okay, guys, the F4 layer, I'm going to look at this one last one. The F4 layer would be a good topic with the atmospheric compression coming during solar minimum. The newly discovered F4 layer. I have to look into that. That's something that it would be difficult for me to talk about until I'm ready for the ionosphere class, which will be a little bit way down the road, because I want to talk mainly to ham radio operators and emergency responders and talk about things that are very relevant to them, not necessarily something that's relevant to a scientist. I'm leaving the science to the scientists. I leave that for my off time and for maybe Patreon members if they want it, like what I did with Parker Solar Probe. But I don't usually do that for the mainstream audience, because I want I'm dealing with space weather practitioners, and I'm trying to serve them because they need to understand space weather well enough to get through their day. So I'll look at that, but I may not talk about that much. You'll be a rock star at the August convention if your propagation class can be contained in 50 minutes. Oh, thank you. That's so sweet, John. Yeah, when these YouTube classes are, a free-for-all, my lectures are very contained and they're very specific, and I don't deviate. So these things are this is what I do for fun, and so I don't mind going hours at a time. But yes, when I'm asked to give an actual lecture, they're very they're very contained. So as a matter of fact, I'm going to have to give one. I'm going to give one to LA Unified School District teachers along with the American Chemical Society coming up on the 16th in Northridge, really close to where I am. And I'm doing a workshop for the LA Unified. These guys are working with high school kids, and we're going to be doing a workshop that teaches them how to look at real-time space weather data and hopefully get their kids interested in space weather as a kind of weather for the new generation. So see, these are the types of things I'm trying to do. If we can educate kids in schools, then they grow up with space weather, and it's not so alien to them. And the idea that it's not on the 6 o'clock news, they'd be like, well, why isn't it on the evening news? Because they learned about it in school. So these are all the things that I'm trying to do. So, okay, guys, I think my voice is going. So I'm going to get off here. When are you ready to go up to the general? Let me know. I can help you with it. Thank you so much. Yes, I have the books. I need to study to get up to the next level. And I know a lot of people tell me, well, I can't talk to you unless you get your general license. I know, a tech license isn't enough. But it's a matter of priorities. So if I only got my license just recently, so I'll get there. It just may take me another year or so. Have you considered how the sun structures our water we drink? No, that's not what I do. So, okay, guys, that looks like that's about it. And I am exhausted. Hopefully you are exhausted. I hope I didn't make you drink from a fire hose. But this has been a lot of fun, and even with all the technical glitches today, it's been a lot of fun. So thanks for hanging in there, and I will talk to you soon. Okay? Bye. And we'll see if I can even stop this. I may not even be able to stop this. I may have to leave the screen to stop it. So if you stare at a green screen for a little while, you'll know why.